टाइम देखि देखि पूरा काले म टाइम एटा भूल हेजो बोली तथापि भी आज मु 8:15 रे बाहरी भी बोली टारगेट रखिथिली सेमे पहुंच पाई Send the list of participants. Department of Chemical Engineering of the University of Korea, the city streams of Korea Institute of Science and Technology, 1994 between 95 to 96, and worked as a research fellow under Professor Alan McDermott of University of Pennsylvania, Nobel laureates of chemistry in 2095, joined Samsung SDI. Was a PhD project at Samsung SDI in 1996 and established its dual beginning in 1997. He is the author of 310 SCI papers and 160 patents in the field of organic semiconductor material. He was also chairman of 12 large-scale projects of Korean Industrial Revolution with electronic materials. He received the Prime Minister President Awards from Korean government in 2012 and joined also elected SPI in February 2018. Also published Department of Chemistry and Center of Technology, IIT Guwahati. He received his bachelor degree in chemistry between 1993, masters in 93-97 in organic chemistry from Bhavnagar University, India, and then completed PhD between 95 to 99 in Silicates and Catalysis Division of Central Salt and Marine Chemical Research Institute, Bhavnagar, CSNCR, Bhavnagar, India. History Department, Chemistry, IIT, then he joined 93 93 Then he joined Department of Chemistry, Israel Institute of Technology, Israel Smith Foundation Post of Professor Fellow for Lady Davis Post of Professor Israel. Then he moved to Center for Polymers and Organic Solid, University of California, Santa Barbara, California, USA, as Total Postgraduate Researcher during October 2001 to 2003. And बाकी कितनी पोस्टर पहुंची
Hello, hello, hello. बोले ना थोड़ा सुनने के लिए सुना
यहाँ पे तुम्हारा ओपन है ना?
हाँ हाँ मेरा 5 साल का
मैं वो लिंक ज्वाइन करूँ क्या?
हाँ कर दो
देखना मैं ज्वाइन
Applications. कल कैसे ठीक खाना वाना खा के आए?
नहीं मैं
इधर मंगाया नहीं था सब कैंटीन से मंगाया नहीं। हाँ क्या क्या बना है बाद फ्री टाइम में जाके
मैं गया था लेकिन उस टाइम ओपन नहीं था।
फिर खा ले केला
तो नीचे वाला कैंटीन ओपन था तो कुछ खाना रखे नहीं होंगे।
नहीं मैं मतलब अराउंड 8:15 को गया था उधर।
अभी आई तो उधर वाला दरवाजा
हाँ
खुला
अभी
है।
मैं भी आया तो उधर से तो दिखा लेकिन अभी वो टाइम इधर हो जाता तो इसलिए
हाँ ठीक है बीच में एक बार जाके सबके लिए खाना लेके आते हैं खाएंगे आज खाएंगे चाहे कितना काम करेंगे तुम्हारा फैमिली इधर है नहीं छोड़ के आए लेके आओ एक बार
फिर देते हैं
कितना कितना मतलब
ये तो मैं
ठीक थीसिस सबमिशन के टाइम में
लेके आया
बेबी गर्ल की बेबी बॉय
बॉय
बॉय बड़ा हो जाएगा तो बेबी उस दिन हम लोगों के साथ रह के जाएगा उसकी दादी बन गए
क्या हुआ?
नहीं हो रहा है कौन सा लिंक ओपन किया है?
मैंने वो
वेबिनार वाला और ये वाला
वो टीम वाला
ओपन किया
हाँ
क्या अच्छा मेरा
हो जी
ये तुम्हें ज्वाइन करना था
कैसे नहीं हो रहा है रे
वेबिनार FOE 282 ना
तुम ज्वाइन किए ना कैसे ज्वाइन किए
है तो मीटिंग जो जनरल वही वाला तुमने
हाँ
तो
मीटिंग
start
इन
किया है ना?
जनरल यस मैम
जो
लेकिन
तो
तो
में जाके कर रहे हो ना
हाँ
ये लिंक से नहीं हो रहा है
नहीं होगा।
तो सेकंड डे का लिंक से ट्राई करो ना लिंक से ट्राई करो ना
लिंक से ट्राई करेंगे
इसको बंद करके लिंक से ट्राई
अच्छा लिंक कौन सा है
तो मेल में होगा ना सेकंड लिंक जो
इसमें भी तो था ना लिंक नहीं था टीम में और लिंक मेल में जाएगा ना
हाँ इसको
अगर ऑफलाइन होता है अभी तो
क्योंकि बच्चे तो सारे लिंक से ही ज्वाइन करेंगे
हाँ हमारा तो भी हम ज्वाइन कर लेंगे हमको तो ले जाएंगे ना वो लोग भी तो लिंक से ज्वाइन करेंगे बाहर वाले, लिंक ही नहीं वर्क
टाइम हो
कर।
गया लेकिन ना
अभी हुआ
हो गया ना
अभी हुआ क्यों?
अभी हुआ
उस टाइम में ज्वाइन नहीं की होगी तुम तो कर रही थी कि
तो वो इंटर नहीं किया क्या ना?
नहीं, मैं सबको पास बाईपास कर दी हूँ।
अभी हो गया।
हो गया ना मैम, आपण भी टिके करिके देखि दियंतु ना।
खाली एप्पल ये ना आईफोन एंड्रॉइड तो खाली कंफ्यूज हो जे इच्छे पे यूजर फ्रेंडली
ସମସ୍ତେ ଲିଙ୍କ ରୁ ଜଏନ୍ କରିବେ ନା ଯଦି କିଛି ପ୍ରୋବ୍ଲେମ। ଆଜ୍ଞା
तो ଏଠୁ ବି ଜଏନ୍ କରିପାରିବି ନା ମୋର ଏତେ ସାଉଣ୍ଡ ସିନା ଆସିବନି
ଖାଲି ଜଏନ୍ କରିକି ଦେଖି ଦିଅନ୍ତୁ ଖାଲି।
हो रहा है ना?
तू तो किया, तू और किसी से नहीं किया ना, भाई लिंक से ही किया ना।
मैं जाऊँ फिर उधर।
अच्छा उधर का
हेलो हेलो
ये
बोल
वाला से ऑन कर दो क्योंकि टाइम हो गया ना हम लोगों का।
उधर तो ऑन है ना?
ऑन है
सब ऑन
उधर
कर दीजिए।
लॉगिन कर दिया टीम
हाँ
में।
हाँ सब कर
नहीं
टीम में लॉगिन कर दो सर का जो
कर दे कैसे।
सेंड मी द दिया छोड़ के पठे के चीज को
हेलो संध्या।
हाँ हेलो।
हाँ संध्या आवाज
ठीक ठीक
आ रहा है ना?
हाँ हाँ हाँ
ठीक है। ठीक है पीछे का दिख रहा है ठीक है।
जयपाल इंतखाब को थोड़ा बोलना कि वो लिंक से थोड़ा ज्वाइन करेगा बोल तो। हेलो गुड मॉर्निंग सर।
ज्वाइन करेगा ना वो?
हाँ हाँ यस सर यस सर। हाँ हाँ यस सर यस सर।
शिवा ने वो लोगों को बोला ना।
हाँ हाँ ओहो अच्छा 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 ठीक है सर। हाँ हाँ मैम है। यस सर ठीक है सर यस। हाँ हाँ ठीक है सर ठीक है सर। लिंक था
संध्या वो इसमें डाल दिया है क्या
क्या?
यूट्यूब में?
हाँ 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 डाल
यूट्यूब
चुकी हूँ। जयपाल थोड़ा इंतखाब को बोलना लिंक के थ्रू ज्वाइन करेगा।
ओके ठीक है।
सर कौन कहले
सर कहले जो जय भारती मैम कही था किंतु कौन कंडोलेंस ପାଇଁ ସେ ଟିକେ ମାନେ ହେଇ ପାରିଲାନି ତ
माइक
ସେଟା ମୁଁ
कर दे
5ଟାରେ ପହଞ୍ଚି
ପହଞ୍ଚୁଛି ତ
କହିଲେ
କିଛି ଅସୁବିଧା ନାହିଁ
हाँ
माइक ऑफ कर दे फिर थोड़ा सा।
କେହି ଜଏନ୍ କରିନାହାନ୍ତି।
ଜିମ୍ରା ଖୋଲିନି ଜିମ୍ରାରୁ ଡେଟ୍ର ଲିଙ୍କକୁ କ୍ଲିକ୍ କରୁଛି ଇଏଟା ଯାଉଛି ମାନେ
एमएस टीम को
ଜଏନ୍
जाउछ
କନଭରସେସନ ବୋଲି ଆସୁଛି କିନ୍ତୁ କିଛି ଆସୁନି ମାନେ କିଛି ଗୋଟେ
तो मैम जॉइन हे जिवो ना माने हबो तो
नेटवर्क एरर ଅଛି ବୋଧେ କି କଣ କାଇଁ ମୋ ଏଥିରେ ଏनଆଇଟି ଇମେଲ ବି ଖୋଲୁନି
कहि देखिया जयपाल को ଆଉ କାହାକୁ ପ୍ରିୟଦର୍ଶିନୀ କହିଦିଏ लिंक थ्रू जॉइन कले हाँ 2-3 जन जॉइन कले जदी ହେଇଯିବ।
ଆମର ସେ ଟିମ୍ର କୋଡଟା ଥିବ ଟିମ୍ କୋଡ ଟିମ୍ କୋଡଟା ସେ ଯୋଉ ଜେନେରାଲ ମେସେଜରେ ବି ଦେଇପାରେ if the link is not opening join for the code ବୋଲି କହିକି
ଯେ ମ୍ୟାମ୍ ସମସ୍ତ ପାଖରେ ସେ
ଓ ଯାହା
ହଁ
ଜଏନ୍ ହଉଛି ତ
ଆସିଲା
କିଏ ଗୋଟେ ଜଏନ୍ କଲା
ଏମିତି ଦେଖା ଜଏନ୍ କଲା ହେଇଯିବ ତାହେଲେ ନା ମ୍ୟାମ୍
ଅଣ୍ଡାରେ ଅଛି ନା
ପାର୍କ
ସେଥିରେ ଆମେ ଇଏ
हो गया
लिंक भेज देंगे इनको ना
यस इंतखाबी वाली लिंक से क्या है ना
लिंक भेज देंगे
लिंक तो भेज दे
लिंक भेज दूंगा तो ज्वाइन कर लेना
हाँ ठीक
ଆପଣ ଲିଙ୍କ
हाँ ଆସିଲା
ଯୋଉମାନଙ୍କୁ ସବୁ ପ୍ରେଜେଣ୍ଟର ବନେଇନି ସେମାନେ ତାଙ୍କର ମାଇକ୍ ଆଣ୍ଡ କ୍ୟାମେରା ଦେ କ୍ୟାନ୍ ନଟ୍ ସୁଇଚ୍ ଅଫ୍ ରାଇଟ୍
प्रेजेंटिंग दे
ସମସ୍ତ
एवरीवन कैन
କଣ ହଉଛି ସେ ଗୋଟେ ଗୋଟେ ପ୍ରୋଗ୍ରାମରେ ଥାଏ ନା
हाँ କରିଦେବି ମୁଁ ଏଥିରେ ଏଭ୍ରି ୱାନ୍ ଅପସନ୍ କରିଦେଇଛି ତ ନିଜେ ହିଁ ମ୍ୟୁଟ୍ ଆଉ ଆଜ୍ଞା
Hello.
ହ୍ୟାଲୋ କହୁଛନ୍ତି ମ୍ୟାମ୍
Takuma.
ହ୍ୟାଲୋ
Hello,
Professor Park.
Professor Park.
Yes. Good morning.
Good morning,
Good
sir.
morning, sir.
Can I test my presentation? Can I try to test?
Hello.
Hello.
Oh, I'm okay, but can you hear me?
Yes, sir.
Yes, sir.
Yes, Professor.
Okay,
Yes,
good.
Professor.
Good.
You are audible.
You are
Can
audible.
I try to test my presentation?
Yes, sir.
Yes, sir.
Please share your
Please
slide.
share your slide.
Okay. Where can start? Oh, hold on. I don't know. Actually, this is the first time I use this team. Okay, here. All right. So, can you see my screen?
Yes, Professor. It is visible.
All right, good. One more thing is that I'd like to check the video files. Can you hear me?
Yes.
Okay.
But okay. Video is also okay.
Let's listen to the sound.
Yes, Professor. It is
All
running.
right,
Video
it is working, right?
Yeah.
Okay, thank you very much.
Will you go that side?
Oops.
Good morning, Professor Park.
Hi,
This
good
is Siva Kumar.
morning.
This is Siva Kumar. How are you?
Hi, I'm fine. Thank you. How are you?
I'm good. Good.
Okay, okay. You are Siva Kumar, right? Okay,
Yeah.
okay, good.
हेलो हाँ हाँ किछ नहीं ହେଇଗଲା ଆରେ ନାଇଁ ଲିଙ୍କରୁ ଜଏନ୍ ହେଉନଥିଲା ତ ମୁଁ ସେଥିପାଇଁ କହୁଥିଲି ଆଉ ଆଡ଼ମିଟ୍ କରିବାର ଥିଲା ତ ମୁଁ ସେଠି ଫାଷ୍ଟର ଲବି କଲି ଯେ ହେଲାନି ଫୋନ୍ ଥରେ ଆଡ଼ମିଟ୍ ଆସିଲା ତ ସେଥିପାଇଁ ଫୋନ୍ କରିଥିଲି ତ ହେଇଗଲା ଏବେ ହଁ ହେଇଗଲା ହଉ ହଁ ଜଏନ୍ କରିଥିଲି ନା କେହି ଆସିନାହାନ୍ତି ମୁଁ ଚାବି ଆଣିକି ପଳେଇ ଆସିଛି ମୁଁ କଲ୍ କରିଛି ଠିକ୍ ଅଛି ସ୍ନିଗ୍ଧା ହଁ ହଁ ସ୍ନିଗ୍ଧା ଟିକେ ମ୍ୟାମ୍ କହିଲେ ଟିକେ ସତ୍ୟକୁ କହିଦେ କି ଲିଙ୍କ୍ ଥ୍ରୁରୁ ଜଏନ୍ କରିବେ ମ୍ୟାଣ୍ଡେଟୋରୀ ବୋଲି କ'ଣ ପାଇଁ କି ଏବେ ବି ଛୁଆ ହେଇନାହାନ୍ତି ଆଉ ତୁ ହଁ ହଁ କହିଦେ ଏବେ ସାଙ୍ଗେ ସାଙ୍ଗେ କହିଦେ ଆଉ ତମମାନେ ବି ଜଏନ୍ କରିନ କେହି ହଉ ହଉ ସାଙ୍ଗେ ସାଙ୍ଗେ କର 9ଟା ହେଇଗଲା ମ୍ୟାମ୍ ହଁ 9 10ଟା ପ୍ଲସ୍ 10 11 12 16ଟା हेलो लिंक थ्रू रु सब जॉइन करो रे छुआ कम अछंती टिके जॉइन करी पका तापर पछा परे माने म्यूट करिके छाड़ी दियो ओके 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 हाँ हाँ ना 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 तमे लिंक थ्रू जॉइन करो ना 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 आ गोटे लिंक पठाई डे 2 रो लिंक अलगा अछि अरे आसी ना मामा मो मेल तो समस्त को करछि काली आउ थरे अरे
Can
रुह
answer it.
एबे बिएडे व्यस्त अछि पठाई
Professor, Professor Park.
Yeah.
Yeah, it's very nice to know you did a PhD in Feist.
Okay.
But after almost 10 years later, I was there, 2007 to 2009, in
Oh,
Department of
really?
Material Science and Engineering. Professor
Oh.
Dr. Professor John,
Who?
Professor John,
Professor John.
Ducking
John?
John. Yeah,
Okay, good. Oh,
yeah,
yeah, it's very nice. Yeah,
yeah.
wonderful.
I spent 2 years there.
Oh, 1 year or how long?
2 year, 2 year,
2
2007
years.
to 9.
Oh, okay.
Yeah.
Oh, it's excellent. You are very excellent.
Yeah.
Yeah, that is the top school, right?
Yes.
Right.
I got my first postdoc there. Then I
Oh,
went to France and then come back to India.
uh-huh. Oh, good.
She's my co-convener, Professor Sabita
Oh,
Patel.
hello.
She
Nice to
also
meet
spent
you.
her time postdoc short period in Korea.
Oh, good. I'm sorry.
फैन थोड़ा आवाज आ रहा है आप बैठ सकते हो उधर एसी में Professor, we will wait for 5 minutes. Is that okay?
Oh yeah, no problem. Thank
Okay,
you.
okay. Thank you, Professor.
Mhm.
हेलो हाँ ମୁଁ କହିଲି ସ୍ନିଗ୍ଧା ଲ୍ୟାବ୍ରେ ବସିକି ଦେଖିଲେ ବି ଚଳିବ या फिर ଆମ ଲ୍ୟାବ୍ରେ ବସିକି ଦେଖିଲେ ବି ଚଳିବ କିଛି ଅସୁବିଧା ନାହିଁ ଖାଲି ସେଇ ହଁ କେଉଁଠି ଆଚ୍ଛା ଆଚ୍ଛା ସେମିନାର ରୁମ୍ ଆଗରେ ଅଛୁ ଠିକ୍ ଅଛି ସେମିନାର ରୁମ୍କୁ ପଶିଯାଅ ପଶିଯାଅ
कर देंगे, हाँ? A very warm welcome to everyone. That today we are going to start our second day webinar on frontiers in organic electronics. I'm very glad that we have with us a distinguished speaker from Jonguk Park from Korea, Department of Chemical Engineering, Yunghwa University, Hengi University, and it's very privileged, Professor, to be host you as a distinguished speaker, the keynote lecture. So now I request Professor Sabita Patel, co-convener of this program, to introduce Professor Park.
Thank you very much, Professor Siva. So on behalf of the organizing committee, I welcome you, Professor Park, to our department as well as to the organic electronics community of India. Professor Park is a professor at Department of Chemical Engineering of Yongi University, Korea. He received his PhD from KAIST, Korea Advanced Institute of Science and Technology during 1994. After that, from 95 to 96, he worked as a research fellow under Professor Alan McDermott of University of Pennsylvania. He is a Nobel laureate of chemistry during 2000. In 1995, he joined the Samsung SDI and received the PhD project award of Samsung SDI in 1996 and established his OLED team during 1997. To his credit, he has more than 300 SCI journal papers in reputed journals and holds 60 patents in the field of organic semiconducting materials. He was also chairman of 12 large-scale projects of Korean industry in relation with electronic materials. He received the Prime Minister and President awards from Korean government in 2012 and 2020 respectively. He was also elected SPIA Fellow in 2018 in the United States as well as in Yongi University Fellow 2019. So with this short introduction, I now welcome Professor Park to this event, to the first lecture of our second day program of this 2 days webinar event. So I welcome you, Park. Please go ahead.
Okay, thank you so much for your kind introduction. Can you hear me well?
Yes, Professor, we are able to listen you.
Okay, so I will show my screen.
Screen shown, then we can. Yes, Professor, okay. Screen is visible.
Okay, thank you. Thank you for answering. All right. Again, thank you very much for your kind introduction. And at first, I'd like to thank the you members for giving me a chance to talk today. As you know, my topic is for the OLED blue emitting materials issues. So this slide shows the title, fluorescence materials with core and side concept, which is related with the TV and mobile phone application. So from now on, I'm gonna tell my research data. Okay, so my talk consists of 5 parts. First, I will introduce the OLED blue emitters issues nowadays, and then I will give 3 topics, class and derivatives, which is related to high photoluminescence, the chromophores. And the second topic is the new core forming method. Hold on, yeah. And the third one is the optimization of pyrene core derivatives. And then I will give summary. Okay, this slide shows the typical representative OLED products from Samsung and LG companies over the world. And there is another application of the OLED lightings. Today I prepared 2 video files. First one is the Samsung video files in the beginning part of my presentation. At the end of my presentation, I'll give another video file of the LG display. So let's watch it for a moment. Okay, I will play. So if you cannot hear the sound, please tell me again.
Sound is coming, Professor, no problem.
Okay, thank you. This video file shows the brightness and contrast and the flexibility and high performance of the OLED. Okay, so just before you watch the Samsung nowadays the display situation, all right, you can actually just search that video in the YouTube. All right, so let's go to the more hot issue for OLED emitters. Actually, the mobile phone technology stage is very high, so we need to develop more in case of the TV application because there is very serious competition between OLED technology and the quantum dot technology. So we need the high performance of the blue emitters, as you can see in this slide. So there are three factors. First one is a higher efficiency. Definitely, it will decrease the power consumption. And second topic is the color purity based on the wider CI value area, tracker area. And number three is the longer device lifetime. So for the achievement of these three main issues, we need to control the chemical structures. Right, so the first topic is the external quantum efficiency. As you know, the external quantum efficiency in device, it can be divided into four factors. Charge balance, we can optimize the 100% charge balance by using some different thickness control. And second topic is the high photoluminescence efficiency Q. And the third one is the exciton ratio, like fluorescence 25%, phosphorescence 75%. And also the first one is the outcoupling efficiency. Even though we make the light, we cannot use all of those. Just only 0.2%, 0.2, 20% can be used. So that's why in the past, we can get maximum external quantum efficiency. In fluorescence case, it was the 5%. In phosphorescence case, it was the 20% in the past. But in 2007, Professor Kido in Japan, he showed the very interesting data, increased the 1.5 times because of the electric field. So after that time, we can change some dipole position and angle and refractive index and birefringence and so on, and organic layer and IT thickness, blah, blah, blah. And then we can increase from 5% to 7.5% and from 20% to 30%. So after that, Professor Adachi, he also invented some molecular orientation. So at the time, I also tried to get the horizontal orientation. So I published the papers too. So anyway, Professor Adachi, he firstly demonstrated the horizontal orientation 1.5 times increment. So fluorescence phosphorescence showed this kinds of the maximum theoretical external quantum efficiency value. Not only that one, but also there is another the chance to change the refractive index of the inside organic materials in device, a cold transporting layer and emitting layer, and even electron transporting layer. So by using low refractive index, we can increase the external quantum efficiency more. And even when we attach the outside of device with the micro lens array or inside the layer between electrode and the organic layer, we can insert some micro lens the configuration. And so theoretically, at most we can expand it and increase the 23% in by using fluorescence case. In phosphorescence case, we can achieve the 90%. So theoretically, it's very high. Okay, so let's go to second topic. That is the color purity. The color, in order to get the high color purity, we need to get the wide CI value area in color coding chart. So if you look at the left chart, that is the CI 1931 year. That is the suggested by the NTSC, National Television System Committee. So by naked eye, we can fill this triangle area. It is defined with 100% color gamut, CRI. So 100% CRI is the just the average retina display for the human. So nowadays, over the world, we are using more than 100%, like quantum dot LCD. In that case, usually we have the 105 or 107, and in older case, we have the 115 and at most 118 something. But we'd like to expand it more. So many scientists suggest another color-coded chart. So by 2020, they'd like to expand this triangle area. By naked eye, even though we cannot distinguish in detail, but they'd like to make the more fancy display application, especially in TV, because it has the huge market. Right, but unfortunately, in 2020, all the scientists failed to get this triangle area. So now even 2022, still the Samsung and LG and other display company people, they are working on the expanded this color coded chart 2020. So in here, especially blue emitter is very important. Especially the Y value is so important. I will explain it again later. All right, so if we summarize just the color purity level, as I said just before, the color coordinate Y values is very important. So for mobile phone case, we need to get less than 0.15, less than, because as I said, in here, we need to go to in blue case, we need to get to the down part. So Y values is very important. So less than 0.15 is for the mobile phone. For the standard TV, you should get less than 0.08. But super ultra high density TV, in that case, we should get less than 0.08 or less than 0.06. So finally, we need to get less than 0.06, like 0.04. All right, the third issue is the longer device lifetime. So as always, for TV case, that is extremely important. In mobile phone case, that is almost solved. Even though we are using OLED TV, that is not fully satisfied with the customer's requirements. So if you look at this table shows just 2012 data. But even though it is you need to check it carefully. If we look at the two primary colors, like red and green, it has the 400,000 and 600,000 and 900,000 device lifetime of LT50. LT50 means the 50% decrease the light intensity. However, if you look at the blue case, just like 10,000 and 20,000, and even 20,000 case, the color point Y value is so bad, like 0.4. It is useless. So in case of the 0.11, it has just only 10,000 hours. So if we compare the device lifetime, there is very serious difference between blue and other two primary colors. Even though that is the 2012 years, so still the same trend is available nowadays. So we should solve the blue device lifetime. All right, so in order to solve this kind of the three issues, we should design and synthesize the new organic materials. So I'd like to suggest the core-side concept. So we worked for the core-side concept materials from a long time ago. That started with like a children's toy, Lego fixture. So at first, we can choose the core chromophore moiety from organic chemistry textbook, and then in that case, we should choose the high photoluminescence material, like anthracene. It has the high photoluminescence PL2I value, and then we can attach the side group in order to tune the property of the final compound by using a symmetric form or asymmetric form. So as you may guess, so during the synthesis process, in asymmetric form case, it has more combination. So it is definitely difficult to purify and separate the materials in case of the asymmetric form. But unfortunately, as always in commercial material, asymmetric material is better than symmetric material. So far we are using all of them organic materials based on asymmetric form. Right, so that's why in my lab from the long time ago, we are working on and we are synthesizing new core and new side and some new different link position approach ways. So we synthesized and published many papers. So the first stage that I'd like to introduce the model compound. As you can see in here, that we choose the anthracene moiety with the high performance, high photoluminescence value. So we attach the side group biphenyl benzene group. So we are saying, as you know, that is the top phenyl group, right? So we can introduce the phenyl ring between anthracene core and top phenyl ring. So we can say that definitely, you know, the triphenyl benzene group. And also we designed and synthesized the asymmetric form top phenyl and triphenyl benzene group in here. And also we introduced the nitrogen atom instead of the phenyl ring in here. So we can change the nitrogen and nitrogen and nitrogen. So as you know, the aromatic amine group, it has the electron donating effect very much. So we can increase the electron density to the core side. And when we introduce the phenyl ring between core and biphenyl amine group, so slightly decrease the electron pushing effect. Instead of that, we can introduce the large bulky side group. So we can prevent the molecular packing and the pi-pi overlap situation. So from the 6 compounds, we found out that there is some difference in maximum values in the range of around 440 to like a 500. Oh, sorry. Sorry, hold on. Hold on. I will try again. Sorry.
Yes, Professor, it is visible now.
Are you okay?
No. It
No.
again.
Okay.
Yeah. Coming.
Okay. Sorry. So anyway, in here,
should see this.
when you change the side group, like the electron pushing effect in here, you can get the relatively longer ER maximum
They are
value.
measuring
So
pass presence.
when we
And another person phone pass presence machine.
when we
Attachable
fabricate the
attachable
device,
so busy.
especially this compound
But anyway, if you are
204, this compound shows the very high luminescence efficiency, like a 10 candela ampere in case of the non-dot device. But other device showed just less than 6 candela ampere, like a 3 and 4. But this material shows a very high luminescence efficiency and very bad the color conic Y value. So trade-off the relationship between the two results. So from here we could understand that when we introduce the electron pushing effect, the EL maximum and the color code Y value is very bad, like a 500 and 0.5 for blue. So actually this is not blue, almost close to the green. But instead of that, we can increase the luminescence efficiency. So we need to handle and we need to optimize those kinds of the property and the chemical structure. So at the time, we were wondering about how can we get the very high luminescence efficiency. So we measured at first the transient ER. So y-axis is intensity and x-axis is time. So when we turn off the light, the fluorescence emission, actually the EL emission, it must be turned off because turn on and turn off. So it must be rapidly decreased, but result was different. Like there was some delayed fluorescence. So what is the delayed fluorescence? Because triplet annihilation generates the extra singlet excitant. So from this the Y value, we can change the some single excitant generation efficiency increment, like a 1.5 times higher than before. And also, we were wondering about the orientation effect between two electrodes. So in this figure, horizontal orientation was described. And when we make the horizontal orientation between two electrodes, this material can enhance the light intensity in molecular level. So by using horizontal orientation, we can enhance the EL efficiency and it can be derived from the bulky side group. When we introduce the bulky side group, it is relatively easy to form the horizontal orientation. So by ellipsometry measurement, we could find some clear data result observation. Actually, there are 4 compounds are here. Median, which was synthesized from the Kodak in the USA, anthracene simple material, and our material 201, 202, and 203. And if you look at the left axis, that is the refractive index. And blue case, it is just the extinction coefficient value. Basically, those are the same. So you can look at just one of two, refractive index or the extinction coefficient. So don't worry about the two things at one time. Right. And if you look at the inside, there is some solid line. That is the horizontal orientation response, and dotted line is the vertical orientation response. So if you look at the two materials at the left, median and 201, there is some dotted response in here. However, in compound of the 202 or 203 case, there is the non-response error in dotted line. It means that only the horizontal orientations are available in device. So from this data, we can calculate some increased outcoupling efficiency like 30%. So that is not 20% anymore. So from this data, we can calculate some theoretical external quantum efficiency value, and you can compare those data with the with the experimental data, like this one. Right, and also actually we were wondering about how can you get the increase the radiative quantum efficiency. So we collaborated with the Kyoto University professor, and then he calculated some increased the dipole moment and oscillator strength. So we can approach some relationship between oscillator strength and the real efficiency. That is matchable, but that is not matched to the not all. It is not always the right, unfortunately. Right. So and then we can change some core system. Just before I said you can choose the one core molecule from the organic textbook. So we are wondering about what about the dual core system. So we pick up the anthracene and pyrene group, which is very famous core molecule, and we designed like four compounds. So dual core system. So we fabricated the device and we could get very interesting data because the dual core system could get like a 2 times increment in luminescence efficiency. So in the beginning of at the time, we thought that, oh, if we increase the core number, we can get increase the luminescence efficiency data, but that was wrong. So because after that we increased like a triple core and quadruple core, but that is not matched to each other. And so we calculated some. Okay, this slide shows the more longer device lifetime data in case of the dual core system. Anyway, we calculated the depth calculation. So as you can see in here, HOMO-LUMO level shows the just electron density at the anthracene group in dual core system. However, if you look at the pyrene group, it has the electron density distribution in case of the HOMO-1 and LUMO+1. However, when we calculate the transition case, there was a contribution level in case of the HOMO-1 to LUMO. So it means that HOMO-1, it has the electron density at the pyrene group. So pyrene is working further and is contributing something to the electron transition in PL as well as the EL. Right, so okay, so next one is so we use the dual anthracene core system too, and we synthesize like the very complicated process, and finally we could get very very high external quantum efficiency, more than 6% without any doping. Actually, at the time we didn't like to change the device configuration because it took time very much. So we would like to focus on just the chemical structures and the basic device performance in order to understand the chemical structure. Right. Anyway, we changed several kinds of the different shape of the dual core system and different link position between core and side group. Right. And as I said, even we expanded the triple core system. So single core and dual core and triple core. So we use the anthracene and pyrene and anthracene, and even we changed some link position, and even we changed some different cores instead of this triple core system. Right. So from this material, anyway, we could get very interesting data like excimer result. And by using ellipsometry, we could get like some horizontal orientation, and it will make some axial result in PL and in EL. So from this data, in triple core system, we could get, I will skip this one, we could get the very interesting single molecular white device at the time, like a 6 candela ampere with the white color coordinate value 0.3 and 0.44. Right, so even we changed the quiescent moiety instead of the pyrene, and then we also could get a very interesting blue performance. Anyway, we expanded the core numbers, but there were some limitations because, as you can see in here, the molecular weight is too high. Actually, it is impossible to evaporate the organic materials when we use the more than 1200 molecular weight of organic materials. So in case of the triple core system, we don't have many the changes the vectors if we want to change the and vary the chemical structures because of the to hide the molecular weight of the molecules. All right, so next topic was the link position. So we were wondering about the link position between core and side group. So here, I described just one simple core chemical structures in the tyrosine. This one, when we calculate the electron density distribution, as you can see in here, number 2, it has the electron rich position, like a row. In case of the number 1 and number 3, electron deficient node position. So we would like to compare the link position with the and the EL performance. So we design and synthesize the 3 molecules. We exact the same molecule core and the side molecules. Just the different thing is in here, number 1 position, number 2 position, and number 3 position. So as I said, number 2 position, from here, there is a meta position. It has the electron rich case. So electron rich case showed a very interesting increased luminescence efficiency. And as I said, when we have the electron rich state at core, it has the worst color point Y value. So EL maximum value shows some redshifted longer wavelengths compared to other 2 materials. Definitely color point Y value is worse than before. So that's why it has 0.79. Other 2 things show the 0.068 and 0.063. All right. So from now on, I will introduce the quiescent derivatives the result. So as I said, when we increase the electron density at core, definitely we can get a higher efficiency of the device. But we can make we made make some worse the color coordinate with the performance. So that's why in case of the Galaxy S1 and S2 and S3 case, Samsung they use the anthracene coil moiety. It has around 300 nanometer absorption band edge. So that is the band energy gap. And in pyrene case, it has the shorter wavelengths like 350. It has the wider spectrum width. So Galaxy 4, 5, 6, 6 and around 7, Samsung they use the pyrene core moiety instead of the anthracene group. So I suggested a new core system, Crysen, because Crysen has the shorter wavelengths compared to other 2 materials. So we have the more wider optical spectrum range window. So we have the more freedom in order to introduce some more electron density side group in here. Right. Anyway, when we check the electron density distribution of the Kreisen group, so all link position has a similar the electron density. So we chose just the simple number 6 and number 12 position in order to make the easy synthesis scheme. Right. So this slide shows just the similar representative model compound chemical structures. So Kreisen is here, and terpenyl group is here, and triphenylbenzene is here, and also same approach ways. We introduce nitrogen instead of the phenyl ring, nitrogen at both way, and nitrogen instead of the phenyl ring in here. So finally, when we okay, before saying the important data, I'd like to show you one more other similar data in here. This slide shows the 3 different kinds of the emitters, but if you look at the inside, we use the same side group, propane group, just we change the anthracene and pyrene and Kreisen. So definitely this pyrene group, TPC-TP, this material, it has the large band gap compared to other materials. So when we choose the Kreisen moiety, it is working to decrease the wavelength, and it can increase the band gap value. So that is very matchable with the real blue or the deep blue material system. All right. Anyway, from the several kinds of the optical data, finally we fabricated the EA device. So when we use the Kreisen moiety, that it was hold on, I need to actually okay, this working. Right. So if you look at the number 2 compound, terpenyl group and triphenylbenzene group Kreisen, it shows very wonderful color coordinate Y value. At the time, it was the 0.042. So it is very amazing at the time because, as I said, super ultra high density TV needs the 0.06, less than that one. So this material satisfied that requirement. And also, when we introduce the triphenyl amine group instead of the triphenylbenzene or terpenyl group, definitely electron rich can be enhanced. So that's why we can increase a little bit more, like a 4.8 external quantum efficiency, and with a little bit worse the color point Y value of the 0.077. But when even though it is we use the Kreisen moiety, that's why we can maintain the around the 0.08 color point Y value. So this data came from the non-dot device. So we trusted this patent company at the time. Right. So we also changed another side group with the Kreisen core moiety, and we developed more than 7% external quantum efficiency with the 0.11 color coordinate Y value. Right. So the next topic is a new core forming method. So as I said, we synthesize the dual core, triple core, and many things, but we should pick up the main core from organic chemistry textbook or the reference papers. So I don't want to do that anymore at the time. So I thought that, okay, conventional methods, just we need to change the functional group kinds substituted into the core moiety, and otherwise we can change the number of such functional groups, and also otherwise we can substitute the various numbers of core moieties. So what is next? So I can suggest at the time this kind of the new core forming method. So if we use some fused core concept with like a phenyl ring, For example, in here, pyrene and fluorine, you can share the two just common core moiety by using share the like this phenyl ring. So we can draw this kind of the chemical structure. So definitely there is no compound anymore in the paper, in reference paper as well as the textbook. So instead of fluorine, we can combine the pyrene with the carboxyl group, so we can draw this kind of the chemical structure. So we design and we synthesize the binary. So we use just the non-fused system reference material, compound A, and compound B and C were synthesized at the time. So finally, okay, so one other thing is that at the time when we use the pyrene group, we use the number 4 and 9 position instead of the 1, 3, 6, 8. Anyway, by using that one, we could get real blue materials with the 300 per ampere. So new core forming method is working in order to make the new core system. So we could get patents and the papers in the past. Right, and at the time also, I'd like to enhance the more fused ring system. So we use the Poisson moiety and the spiral fluorine group because I'd like to amorphous state based on 3D structure because the organic emitters can be evaporated with the amorphous state in real device. So as you can see in here, we could get some two different kinds of the symmetric and asymmetric 3D structures of the new core forming method. So finally, we could get the blue performance, even though that luminescence efficiency is not so high. Anyway, we can draw and we can design the new core system by our own approach way. Right. The last topic is the optimization of pyrene represented to core moieties. So we synthesized several kinds of the pyrene derivatives with the different kinds of the side group. So in detail, I'd like to optimize the side group. So as you can see in here, this is the reference material, just biphenylamine group. So in here, I use the RT group one by one, and finally, actually we designed many kinds of the side group, but we optimized the this side group for pyrene moiety and one tertiary butcher and the methyl groups and number and position. So when you fabricate the device, it shows very high luminescence efficiency, more than 10 candela per ampere with the mobile phone specification. So we checked the device lifetime at the university. We could get more than 1,000 device lifetime. So we started to collaborate with the LG Display at the time. So we received some more advanced other hole and electron carrier materials from LG Display. So we could get more fancy device structures for getting long device lifetime. And then finally, we could get more than 30,000 LT50 device lifetime. So we, at the time, the Samsung also, they measured this material and they got the more than 45,000 device lifetime. But the mobile phone specification was the 20,000, so it's too long. And we wanted to use our material for real Galaxy S9 or S10 mobile phone. But at the time, unfortunately, new Davna multi-resonance material came out from Japan. So they have the like 25,000 and close to 30,000 is the more than mobile phone specification, but their materials has the 2 times the higher external quantum efficiency compared to our material. So that's why our material just exported to China main factory. All right. So finally, we can add the one more line in here, like a 30,000 device lifetime. All right. So in conclusion, I'd like to say, number one is the new Christ-Code derivative showed a very deep blue emission for super ultra high density TV application. And secondly, new fused core preparation methods were realized. And we optimized the parent derivatives and issued the luminescence efficiency of the more than 10 candela per ampere and the 30,000 device lifetime. Okay, so now that I will show the another second video. Let's watch it. Okay.
디스플레이는 끊임없이 진화하지만 결코 변하지 않을 가치는 사람을 향한다는 것. 한 장의 디스플레이로 마음까지 감싸며 소통과 치유의 가치를 담아 우리의 꿈에 더 가까이 다가갑니다. 소망하던 것들이 펼쳐지고 그 공간의 모든 감성이 오감으로 전해지는 놀랍고 소중한 경험.
Sorry for Korean language.
우리는 그렇게 다음 세대의 행복을 키우며 더 새로운 세상으로 나아갈 것입니다. 누구나 꿈꾸는 미래, 그 미래를 현실로 만드는 기술. 모두의 상상을 넘어 올레드가 열어갑니다.
Okay, so it was the LG Display's OLED future samples. Okay, all right. So as the professor introduced my result, we published 348 papers and more than 60 patents. And I have many collaboration partners, as you can see in here, and my lab members and many funding sources. All right, thank you very much for your attention.
Thank you, Professor, for your nice and informative talk. Now we'd like to hear from the participant, 1 or 2 questions. Professor Park is ready to, clarify if you have any such, any curiosity to know.
Hello. Sir, am I audible?
Yeah, you are audible.
Okay. Sir, thank you, sir, for the nice informative lecture. So my question is regarding the anthracene as a single core system. If we substitute anthracene at 9-10 position with the phenyl group, so if we substitute that phenyl group with the donor at the meta position is more favored as compared to the ortho and the para. Why it is, sir? Can you, sir, give me suggestion regarding this one?
So actually, sorry, I lost in the beginning of you were saying regarding which category? I'm sorry about that.
Sir,
Sorry.
anthracene as core system.
Anthracene and what?
Yeah, anthracene as a
Professor,
core single.
Professor, in the anthracene system, the substitution of phenyl ring.
Phenyl ring.
Yes.
At 9 and 10 position.
Nah. There are so many anthracene derivatives in here. So
could you please
can you
slide
remember
number?
the page number?
Yeah.
No? Can you remember the page number? No?
So 9 and 10 position of the anthracene.
No.
We substitute
Nah,
that
no,
position.
no. Hold on.
Slide number. Please tell that slide number.
Yeah, slide number.
I don't remember that slide number, sir, actually.
Yeah, early part of the presentation or middle?
Yeah, sir. Early.
Otherwise, I will show the presentation.
Yeah, Professor, okay? You can go to some meta substitution, Professor. Like meta, you have given some greater than like one slide, or 10 or 15th slide, I think.
Can you see my screen now?
Yes, sir.
Not Professor.
Sorry, can you open that slide number 20? So here I can.
20?
Slide number 20. 20, Professor.
Yeah, 20 is that one, actually. No?
This is 20.
Yeah,
yes.
It takes, yes.
Sir, here, this phenyl ring is attached with anthracene at a 9 and 10 position.
Yeah.
So here is this 3 phenyl ring is attached at the para position of this attached with the phenyl ring. So what is the effect when it will attach at ortho and the meta position?
Oh yeah, you mean right? Yeah, okay. So now I can understand what you're saying. So if we use the meta position, definitely the emission wavelength will go to like a blue emission. So we can make the more deep blue and good color purity, but as you know, when we use the meta position case, the electron pushing effect will be decreased. So definitely the luminescence efficiency will lower down. Okay?
Okay, sir.
Okay, thank you for question.
Hello, what's your name?
Yeah, Malesham, please go ahead.
Yes, sir. What's your name? This is Malesham Godumala. Annyeonghaseyo.
Oh, yeah.
I know a little bit Korean because I was there in Korea for 4 years with Professor Dangun Chai in Korea University.
Okay.
Yeah. Thank you for your presentation. Just I have some question that anthracene and pyrene are only useful for conventional fluorescent emitters, but not for TIDF. Nowadays, the complete trend is depending on TIDF only. So how we can overcome this problem?
You mean TIDF issue?
Yes, sir. Anthracene and pyrene only for conventional fluorescent emitters, not for TIDF. Not for TIDF. We cannot decide. We cannot design TIDF materials depending on anthracene and pyrene.
Yeah, of course. In order to make the TIDF result, as you know, definitely we need to very narrow the gap, the energy gap between singlet and triplet. But when we use the fused ring system like a carbazole,
yes, sir.
Like a carbazole, like anthracene and the pyrene group, that the delta ST is too large. So
yes, sir.
Yeah, so we cannot use that one. So because as you know, we need to make some. Hold on, I will show that one. Another example. Hold on. So hold on. Sorry about that. Now you can, for example, you can watch my screen, right?
Yes, sir.
So if you look at this, the Homo and Lumo level, so it has the localized anthracene together. So it should be separate. But this is overlapped very well. That is the localized excited early state. So in this case, we cannot make the TADF. So in order to make the TADF phenomena, Lumo level move to other way, like here.
Yes, sir.
So when we use the anthracene and pyrene group, so unfortunately we cannot make the charge separation. So that is the overlapped situation. So that's why we cannot use the anthracene and pyrene moiety in KDF. Sorry about that.
Yes, sir. That's why my question is, we cannot design TADF materials based on anthracene and pyrene. So do you think still anthracene and pyrene have future in OLED technology?
Yeah, right. Because the another disadvantage, serious problem of the TADF, there is a lifetime, device lifetime. Because when we change the the electron density location, like a left side and right side, so electron density, HOMO and LUMO level have the different location, so it will make some charge accumulation by disadvantage during device operation. So that's why it is extremely difficult to get long device lifetime in case of the TADF.
Yes, sir.
So that is a problem. So there is the actually not problem. Actually, there is a big hurdle to overcome that device lifetime in case of the TADF.
Yes, sir.
So but multiple resonance is different. So basically, in my personal opinion, multiple resonance boron compound is quite okay to the future. But in TADF, it has the huge big hurdle to overcome the device lifetime. Even though we get the very high the external quantum efficiency by using TADF, because as you know, we can get regenerated exciton very much from the TADF. It's good. I'm 100% agree with that. But it comes from the charge separation, and it will make some charge accumulated situation in device. So it is very, very bad to make the long device lifetime, I think. Sorry about that. Yeah.
Thank you, Professor, for your.
Thank you.
Yeah. Thank you, Professor, for your nice explanation about the difference between the TADF and normal fluorescent material. Of course, you have gained a lot of external quantum efficiency, almost greater than 5%, so which is a great advantage of having the fluorescent molecule. So please join with me to thank Professor Park for joining his busy schedule in Saturday and engaging us almost 1 hour talk.
Thank you very much. Thank you very much.
So hopefully we will see you in person in India sometime, Professor. Maybe next year or something.
Thank you. Thank you very much for your saying.
Thank you.
Okay. Thank you.
Thank you.
Mm-hmm.
Yeah. So very good morning again. Now we have the second talk from Professor Parameshwar Iyer from IIT Guwahati. It's my privilege to invite Professor Parameshwar Iyer. Now I call upon my colleague, Professor Sabita Patel, co-convener of this event, to introduce Professor Iyer.
Thank you, Professor Siva. Good morning, sir, and good morning to all of you. Privilege to read upon the biodata of Professor Parameshwar Iyer. Professor Iyer received his PhD in chemistry from CSIR, MCRI, that is Central Salt and Marine Chemical Research Institute from Bhavnagar, India during 1999. He did his postdoctoral research in Technion, Israel during 1999 to 2001. Then he moved to University of California at Santa Barbara, USA during 2001 to 2003 and Case Western Reserve University, Cleveland, USA during 2003 to 4. In 2004, he joined as a faculty at IIT Guwahati, where he is currently as a professor in chemistry since 2013. He is also the dean and public relation of his public relation, branding and ranking at IIT Guwahati since July 2019. His research interests include the design and development of functional materials and their applications in photovoltaics, LED, transistors, memory, sensor-based device fabrication, and in therapeutics area. He has guided 27 PhD students and several postdocs, masters, bachelor thesis students. Almost 30 PhD students are now working under his guidance at IIT Guwahati. He has more than 200 international reputed journal publications, 11 books and book chapters, 26 patents, and is involved in a multinational startup company, 2 national startup company, and transferred several technologies to industries. He is also associate editor of Nature Scientific Report and Frontiers in Medical Technology and an editorial board member of ACS Sensors, ACS Applied Nanomaterials, ACS Applied Biomaterials, and RSC Material Chemistry Frontiers. He has received several national and international awards and serves as an expert members in various national and international scientific bodies. So, with this short introduction, I now invite Professor Iyer to start his presentation and to address the gathering. Thank you, sir.
Thank you, madam. Thank you. In fact, it was a very long introduction. And I also would like to thank Professor Siva Kumar. I'm trying to load my slides. Somehow I don't know why it is not coming up.
Share the screen, Professor.
Yeah, I did that only actually. I just opened that and the slide is also open. Somehow it is not coming up.
Okay.
There is also an issue. It's raining here and we have some connection issues. In fact, till 10 I could not connect also. Right now also I loaded it actually and it's not coming up. Yes.
You can share the screen rather than loading, Professor. Just share you open the PDF. I mean PPT.
Yeah, it's
then
open.
Just
yes,
share,
open.
Just share from this one. From share and then go to that window. Yes.
Top ribbon, right hand side, top corner.
Share and then yeah. Yes, Professor. It's
Is it coming up now?
Yes. Yeah.
Yes.
Is it full screen?
Yes, Professor. Not yet. Now it came, Professor. Can you move one slide, Professor, and then see one more time?
Just a minute. What I'm doing is I'll try to close down my camera actually. Probably that will help in. It is very slow. I can also realize that it is coming up very, very slowly.
Okay, Professor.
Is it visible on full screen?
The slide has gone, Professor. We are not able to see the screen now.
We are not able to see the screen?
Once again you share, Professor. Now it can.
Is it visible?
Yes, Professor. Coming. Not yet, but it will come. Yeah, visible, Professor. Full screen, it is visible, Professor.
Visible, yes?
Yes, Professor. Please go ahead, Professor.
Okay. Thank you once again, Dr. Siva Kumar. I know IIT Roorkee is also part of this initiative, so I would also like to thank, I think, Dr. Justin, who also is one of the organizers, and the entire organizing team for inviting me to be part of this webinar. I should first begin by apologizing to Dr. Siva Kumar because he has been inviting me and talking to me, but due to my administrative responsibilities, things have become very, very difficult to spend time during the daytime in my office here. And you all are aware that yesterday our Honorable Prime Minister had the Pariksha Pe Charcha program, and I was taking care of the entire Northeast, in fact, with everything. So yesterday, whole day, I could not be part of this event, which really is a big loss to me. And I really apologize once again for not sticking to my commitments. So Dr. Shivakumar, please excuse me for this. I hope that in future, I'll be more this thing. Once I say, I like to be part of that. Once again, thank you for inviting me, and thank you, madam, for the very elaborate introduction. So I have put up the title as perovskite and polymer photovoltaic devices. But if time permits, towards the end, I will also briefly give an introduction of LEDs also. I did not put up slides on LED perovskite LEDs, but I'll show you, what efforts we are making towards the light emitting diode based on these conjugated polymers. So I am though primarily affiliated to the Department of Chemistry at IIT Guwahati. I am very fortunate to also be part of the Center for Nanotechnology. And last year, IIT Guwahati has opened 5 different schools in IIT Guwahati. So, one of them is the Health Science and Technology, which in fact came out as an offshoot of the Center for Nanotechnology, where we started, making biomedical devices, and we ventured in a big way into the healthcare healthcare area, therapeutics, and also making a lot of electronic wearable devices. And that is where, there was a need to integrate more of this health aspect, and to, attract more funding from various agencies like ICMR, DBT. This is where, we got a lot of health professionals, pharmacy background faculty also recently. So this is a very big, move. In fact, this has also gone one step further. The School of Health Science and Technology, IIT Guwahati, probably is going to be a second IIT, where we are also opening the school for medicine. And we are very fortunate that the Assam government is going to be partner for that. So this is also the first example where a centrally funded technical institute like an IIT, will be funded in a big way by the state government. So Assam government is likely to, give us funding to several hundreds of crores to set up this school for medicine. Probably from the next academic year, we'll start with primarily focusing on masters, MS, MD, along with PhD or joint degree program. So this is a very unique thing. But as a chemist, as a person working in material science, this is a big benefit for us, because a lot of materials that we all make, we all maximum that an academician, as an academician, what we do is we make devices, or we try out some biomedical devices or the energy-based devices. And chemists, they only try up to the in vivo studies. Okay, but if we have a healthcare system within our ecology, probably we can go to even deeper, or you can do more elaborate studies. So with this, few words of introduction on my affiliation and how we have grown, I would just like to give a brief introduction on why this is important, perovskite and polymer-based devices. And definitely, there is a thrust in renewable, the sustainable development in all aspects. And one of the areas is definitely energy. Is the second slide visible?
Yes, Professor.
Yes, Professor. Yeah. Thank you. So, these are the 17 SDG goals that are brought out by the United Nations. You all are aware about this, definitely. One of the biggest efforts that comes up from our group is from the goal number 7. We also focus on goal number 6, the clean water and sanitation. But today I'll focus primarily on this, goal number 7, that is affordable and clean energy. And when you talk about affordable and clean energy, you have the renewable energy forms and the non-renewable energy forms. And among the we are trying to move away from the non-renewable energy forms, and these are India-specific, targets or the goals that are there. In this, the government claims that nearly 84 or nearly 85% of the people have access to electricity. Okay, so this is a a very, very large number, and if these numbers are believed to be true, it's really a good achievement for a country like India. Similarly, they also claim that nearly 100% villages in the country are electrified. Okay, as senior, but the reality is not true actually. The very next point they mentioned that although the power cables from the electricity grids, they have reached a transformer in every village, they still have some data where they claim that more than 31 million houses still lack access to electricity. So when you tell 31 million, if you think that each household has at least 4 people, you can imagine that the number of people without electricity, is very, very high. So it is our responsibility to move towards the realizing these goals that the country has said that we should have a clean energy, and the renewable energy are basically even affordable, and if it reaches to the all citizens of the society, probably it's going to be very, very good. The government has also set a very ambitious target by the end of this year, okay, by 2022, that among the renewable energies, the total energy we use, 175 gigawatts of energy, it should come up, through the renewable sources. And when you talk about renewable sources, the focus of the government on 4 different aspects. The first is the solar, where the target is to achieve 100 gigawatts of electricity generation through solar cell. The second is through the wind, where around 60 gigawatts energy is planned to be generated through this, the wind turbines. The third is from the biomass. Okay, this is another major area where still a lot of things can be done. In fact, this number can be even bigger if we tap the huge bioresources that is available in the country. Okay, so this is set as 10 gigawatts, and the last one is on the hydro. Okay, here also definitely you all are aware about the electricity generation from flowing water or the waterfalls. Okay, here the target is of 5 gigawatts, but definitely there is a potential where here also we can have the number can really go up in a big way. But anyway, if you see among all, even if you combine the other three, the capacity is not equal to even the solar. That means there is a huge shift or paradigm shift of moving towards renewable energy, and definitely the solar is one of the major area where there is a focus on the government. For the audience, I would also like to inform that the government of India, both from the Prime Minister's Scientific Advisory Body, all the major scientific advisors, and the Planning Commission, Niti Aayog, that is there, right from the month of from the end of December, there was a huge meeting where it was decided that a policy shift. A policy shift on utilizing.
PPT is not visible.
Sorry?
PPT is not visible. Maybe some again reshare, please.
Professor, you are in second slide.
Yeah, I'm in second slide, correct.
Yeah.
I have not moved the second slide.
Yes, yes.
Is the slide visible? Okay. Yeah, so there is definitely a huge thrust by the government on replacing this silicon over the next 1 or 2 years, and get into the mode of manufacturing of perovskite and the polymer based solar cells. So that's a huge thrust, and definitely the academy, as academicians and as industry, this thing partners, we have to move toward that direction where we can translate our laboratory research and get into the the manufacturing mode where at least small panels for small applications, if not the rooftop applications, we can reach to a certain level where we can actually demonstrate of utilizing these perovskite solar cells. I'm on slide number 3. Is it visible?
Yes, Professor, it is visible.
Oh, thank you. So the technology from the silicon solar cell has definitely moved forward. There are various aspects of these devices. I'll start with the dye sensitive solar cell. This area came up in a big way in the early 90s. Gretzel's contribution is really remarkable, and what happened is over the years, these areas saturated, and the value that they obtained, the best devices, was only close to around 13 to 14%, and that is the reason that the interest in this area has slightly come down. Of course, they are utilizing various these perovskites and various other organic molecules to try to improve, but what has happened is the processing abilities and the advantages that other areas have come up with, are not being able to match with DSSC. In fact, the Gretzel's group has also demonstrated like smart windows, and they have replaced a lot of the normal rooftop solar with the glass buildings that are there. They have replaced the glasses with the solar cells, and they have demonstrated that this can in fact come in a commercial in the market also in a big way. However, the advantage is that these two areas have generated in the past 2 years. It is so remarkable that the entire attention of the researchers, both in the field of materials development and the physics and the electronics engineer who are fabricating these devices has, that focus has completely come on this. In the area of this, organic and polymer, this solar cells, what has happened is when the molecule was, or the polymer was poly 3XL thiophin, the power conversion efficiencies were only around 6 to 7%. But with the introduction of, very unique structures and donor acceptor systems, okay, the previous speaker also introduced very nice donor acceptor systems. In this case also, the efficiency last year saw a huge improvement and it has gone close to 19%. By the end of 2022, this number is likely to probably even cross higher, and we may reach up to 20-21%. So you can imagine that even with 10%, the industry was ready to take up this in a big way to manufacture the solar panels. Similarly, based on the beneficial properties of these conjugated polymers and organic molecules, another area which came up just in a decade or little over a decade is the metal-headed perovskite, or the hybrid perovskites, or the inorganic perovskites. In this case, what happened is, the changes that were introduced in this system were not very large. I will show in the future slides, what were the changes made to the structure. And just, in the last year, we saw a very nice report where the efficiencies has gone to 25.6% and the certified value of around close to 25%. Okay, in our group, the values in the bracket are the values that we have obtained in our lab, and this value is definitely likely to improve to 22 to 23% within the end of this year in our group also. Another area which has come up in parallelly along with this is the tandem solar cells. For the young researchers who are there, when I talk about tandem, it can be a combination of two different technologies. So this can be the existing silicon technology along with the perovskite, which has given close to 29%. But this tandem can be a combination of between a polymer and a perovskite. It can be a polymer and a silicon, or any other two devices. So as such, it is a fabrication. It's like almost like you can say like almost 2/3 of each of the devices fabricated. You bring along these two devices, and you make a tandem device, and you operate it like any other device, and you get the efficiency. So this is another very attractive area. Presently, we do not work, but there is a lot of interest across the world to also take up this area of research, and those interested in studying or knowing more about this can refer to the paper that I have mentioned below. Now, why is this area, both this organic and the polymer solar cell and this metal-headed perovskite, very interesting? This is because they possess a lot of different advantages, like the production cost is very low. They are usually very transparent, as I have shown here. And when I talk about low production cost, that means whenever I'm making a device, okay, as the structure I have shown here, most of the layers, to fabricate this, they are done usually either by a printing method, or you can use a solution. Directly you can process it from a solution, from an organic solvent, and you can use spin coating technique, you can use drop casting technique, you can use, when you go to the higher level of manufacturing, you can also use the doctor blade method. You can use directly drop casting, which is a very, very common method in the industry. In fact, we are also talking to two industries. They already have a setup where they have they print on 2 feet by 2 feet or even larger area tiles, multiple layers, and all the things that I've shown here, they can also print up to 6 layers. So they have ink tanks, you have liquids. By pressure, they suck the ink, they drop it like a waterfall over a surface, which is, moving over a conveyor belt. So the device substrate moves. So that is where the entire the production is saved, and they get back the liquid, and the device, whatever is there, they are dried by hot air. So it's a continuous process, and of course in the case of perovskite, you have to do it in with a lot of precautions. I'll come to that point also to get a very stable device. Importantly, you can also tune the color, and when I talk about the color, it's not just the color, that is visible on this slide, the multiple layers, but you can also tune the band gap. Okay, so you can tune the band gap, and you can match the different layers to have proper charge transfer, the charge separation, and you can get the desired absorption or the emission colors for the LEDs also. Importantly, they can be made on this flexible substrate. So you can fabricate the device on any plastic, paper, or any other transparent surface to get whatever device you want, and you can embed this device on any portable appliances. It can be a mobile phone, it can be on a fabric, it can be on a bag, or it can be on toys. or wherever you want, you can, or even in rickshaws, that is the biggest demand that we are getting, that can we have the solar, there are a lot of rickshaws which are operating on EV, can we also put solar panels on top of these rickshaws to begin with, so that you can have more this renewable source, and the rickshaw driver who is there, he doesn't need to charge it during the daytime. So this is an additional value addition to the existing technology of the rickshaws. And definitely, they're lightweight, as I mentioned, because they can be made on plastic, they can be made on even simple glass, or any other thing. And this is what but takes up these two technology higher than most of the existing silicon-based technology, or any other technology that is there. And definitely, if you go to industrial scale, what we get to know about from the industry now these days is, they want to take up automation, because this is going to really reduce the cost, but there is also the reproducibility. So this is a very important aspect, which has to be introduced. We are also trying to do it in a lab scale, where if we introduce even small automation in 1 or 2 step fabrication, that will not only bring about more uniformity, but probably we may also be able to develop devices which are can be done by multiple people at any given location. A lot of aspects of simulation and AI is coming up into the device modeling. We are also trying to introduce this, to study what is the effect of different additives even before doing it in a practical way. So this is a very important aspect that we are bringing into our studies also, so that we don't need to screen so many molecules. I'll be showing that also in one of the slides, to improve the performances of the solar as well as the LED devices. AI is coming up in every sector of our human life, not just the devices. So we are utilizing this specifically to understand the morphology, or what kind of additives are bringing about changes in that. So this is an initial effort that we are making in our lab, with a startup company, and let us see how much successful we are in incorporating the AI-based data in fabricating this device. And as a chemist and all, it's always our effort to improve the materials. We employ various synthetic routes to improve that the material properties, and definitely we have a broad scope of characterizing the materials by improved technology or improved techniques, and combining all these things, we hope to improve the overall device performances. And this is typically a device architecture. We use a substrate. It can be a glass, it can be a plastic substrate. It is usually commercially purchased with a coating of either ITO or an FTO. We have various charge transporting layers. Can be HTL, ETL, depending on the device structure. It can be a normal or an inverted structure. Even active layer in the solar structure, we have a so this is the active layer, is the main layer which is responsible for the performance of the device, and it is necessary that we have appropriate materials here, along with the combination that I've shown here, either the ETL, HTL, or the buffer layer, which is usually used to either separate from the metal electrode, or it is also used to as a passivating layer. I'll explain what is the passivating layer in the next few slides. Okay, so the passivating layer, it helps in giving protection to the active layer, as well as as a sort of a barrier for either humidity. We put it down, it can be a barrier for even the UV light. So this is how a multi-layer device is fabricated, and there can be more layers, there can be lesser layers. Certain materials are also combined with this active layer to improve the performances, and most of the layers, as I mentioned, at least 1, 2, 3, and these 4 layers, they can be processed from solution. The metal is usually deposited by this vacuum evaporation or the thermal evaporation method, and this is how you come up with a device architecture as desired by a researcher. So this kind of materials, as I mentioned, they have not only application in solar cells, but also applications in a lot of other interesting areas like LEDs, light emitting diodes, OLED, organic light emitting diode, the perovskite light emitting diodes. Similarly, you also have this FET devices, which can be further utilized for various applications, including sensors, chemical and biological sensors, and a lot of other applications. You have the memristor devices. We also work on this. The memristor device is a very interesting area, and not very difficult to develop memristor when you have this technology. Similarly, we also have the surface acoustic wave devices, SAW devices, which are sort of a pressure sensors. A small change on the surface in the presence of molecule and gases or anything, we can easily recognize with the help of these kind of molecules in a device. So it's an interesting area. The scope is not just limited to solar cells, but others interested in multiple areas, and definitely think of utilizing these active layers, the perovskite or the polymer based active material in so many different applications. I move forward. I'll not go into the detail of this. So we started with the first generation solar cells. You have this crystalline, monocrystalline, and polycrystalline this solar cell, and you also have the gallium arsenide based solar cell, and the efficiencies were quite high, but the process to manufacture them is very, very expensive. That is where the technology has moved forward, and we are presently somewhere in this place. I did not discuss about the quantum dot based solar cell. This is also another interesting area, and many of you probably would be working in this area, and it has also seen a growth, and presently close to 18 to or more than 18% power conversion efficiency has been reported. I did not put here the tandem solar cell, but that's another area which is a combination of either of this, along with either combination of this or with the silicon solar cell. So those interested in this area, this is a very nice developing field, and a lot of interest across the world to be part of this effort to generate energy in a clean manner. Forward to slide number 5, I'll just speak a little bit about the polymer solar cell. And as I mentioned, as chemists, we always make efforts to improve the synthesis and see how we can influence the performance of the device. So I did not put the structure of the polymer. This is a PTB7 TH. This is a very interesting polymer, donor-based polymer system. And what we did was, rather than utilizing either a Stille coupling or a Suzuki-based coupling method, we have utilized the method using the microwave. Okay, so in this case, we provide 150 watts per this microwave power at 150 degrees C. And what we do is, in this case, we modify we just vary the reaction time. Okay, so the reaction time is varied from 25 minutes to around 45 minutes. And we also make the same polymer with the thermal treatment method. And what we see is that the polymer, usually this is how it comes up. If I make a film, usually I can peel off into one single layer, which is a very nice polymer. Almost people working on the polythiophene, it is very similar. You can peel off this polymer, and you can get one single film, standalone film, which can be peeled off and you can place in different device or a different area. So it can be obtained in high purity, and we can vary the molecular weight. It can go up to more than 2 lakhs. From around 50,000 to 2 lakhs. And what we see is, when you fabricate this device utilizing this PTB7TH, we can get a power conversion efficiency of more than 8%. Okay, whereas the thermal one, it gives an efficiency of around 7.91%. In this case, even the polydispersity index that we get is quite low, and this can be scaled up to an industrial level, which is usually not possible with the thermal layer. So the thermal method. Okay, so microwave in that way, it allows you to do the synthesis in a larger scale, and you can get very uniform polymer, which is practically not possible with the thermal method. We now in this case we use the same polymer. We change the processing conditions. The previous case, we have fabricated the device at room temperature. In this case, we improve we modify the temperature. We do the fabrication at 40 degrees Celsius, and the thickness also is quite higher, the film thickness, and we combine it with this PCB7. This is how the hot casting method we developed. As I mentioned, the ITO is there. We have the period PSS. We have this, and we deposit both calcium and aluminium. And now from 8, little above 8, we can go to more than 9%. So you can see a small change in the fabrication process. We can change the morphology, and we can that definitely influences the power conversion efficiency, and we can easily improve from around 6 to 7 to more than 9%. So simple polymer, obtained by this microwave method. You have the donor acceptor system, and we can go up to more than 9% efficiency. This is how we now change the synthesis and introduce various other factors here. In the case of PTB7TH, we introduce a molecule. We had the phenyl molecule. Instead of that, we introduce a molecule with 2 fluoride groups. Okay, so when we have this 2-fluoride group, you all are aware that this definitely improves the hydrophobicity, and we change the ratio of the additive that we add, around 0.05 and 0.1, and you can see there is already a change in the morphology of this film. There's also the change in the twist angle, and that really influences the performances. And in this case also, again, we have we see and the improvement in the performance. We have not done this by hot casting method. At normal also, the room temperature processing, we get more than 8% or close to 9% is power conversion efficiency. Whereas the other also, one with the PTB7TH, here also we have seen an improvement of close to 8%. Whereas when we go higher, the M2 polymer, when that concentration of this increases, in fact we are seeing a drop. So utilizing this appropriate quantity of this additive, or the molecule which is part of this backbone that is used for tuning, that is also very, very important to generate this high power conversion efficiency. But definitely when we use this difluoride in this system, what we see is definitely an improvement in the hydrophobicity, and the stability to humidity, it is enhanced. Since we got good results or promising results with the difluoride, we have also made molecules with that we change the position of the fluoride. Now we have the fluoride on the same side. We have all the four that is replaced with the this fluoride. Okay, in this case now we again change the parameters, and we also have done the studies with the non-fullerene these acceptors. Okay, so we have used this PCBM. We have also used non-fullerene acceptors along with this. And we have definitely seen an improvement even with the non-fullerene acceptor, and we have gone close to 9.5% with M1 polymer. Whereas in this case, we are able to go up to even with ITAC more than 9%. So this is a very important development. We have used BCP here. That's an additional additive that we use in the device engineering, which was not used in the previous step. So small additives to the device architecture, small changes in the backbone, including we add and separate donor acceptor system, different combination of donor acceptor system, ITAC, which is much economical compared to this PCBM, also gives a very, very good result. So this is what is very, very encouraging for all of us to utilize or change the structure, the backbone, have other molecules incorporated in the structure, and develop systems where you can get very high efficiencies. You can tune other parameters and make these devices even in large area. I'll be talking about the large area devices when I go to the perovskite, because the performances there were much higher, which encourage us to go to this large area devices there. I move forward from the perovskite, from the polymer to the perovskite. For those of you who are not familiar with this area, this was this material is named after a mineralogist from Russia. It's called the Lev Perovsky. However, it was discovered by other scientists, Gustav Rose, and typically it's a structure of CaTiO3. So we call it A, B, and X3. Okay, I'll be showing that how this has been replaced. The CaTiO3 has been replaced by other materials. The typical inorganic oxide. We can put organic materials here, and just after the first report in photovoltaics in 2009, in the last 10 to 12 years, this has really matured and competing with all other areas. And definitely, these are all the applications that are possible with this class of materials. Okay, I already discussed about this. I'll not again mentioned. I'll not again go into the detail. So this is the structure of the polymer, which has given this 18%. So those of you who are interested to pursue this area, this is called D18 polymer. Okay, so and the PTB7TH, this is what we use. There's another polymer called PBDBT polymer, where also you have more than 10%. So there are a lot of polymer-based structures, and there is a combination of the PCBM also, and as well as non-fullerene acceptors, which are utilized for developing this polymer-based architectures for getting higher efficiency. So these are the advantages. I'm not going to again the details of the same thing, but definitely these are the same advantages which are also there with the perovskite-based solar cells. I move forward. This is a typical structure, as I mentioned, ABX3. You have this, A, the B, and the X3. You can clearly see that A is the cation, which is placed usually in the center, but it can also be on the edges here. Okay, the B again is it's in the part of this this cubic structure, and you have this X, the small, the violet color, which are there. This sit on the edges of this, cube, and you can have a large combination of different materials here. I'll be showing the next slide. What is this A, and how we can also use it in combination with other things to improve the properties in terms of stability and performances. Okay, and when you do that, what happens is you can obtain higher absorption coefficient. You also get this broad absorption range. This is one of the reasons where these materials have generated a lot of interest. Most importantly, they are also getting incredible carrier these mobilities, and you can make ambipolar devices. They are also utilized now in a lot in these ambipolar transistors, and that has diversified their application to various sensors and a lot of other applications. And the tunability in this case is much easier, even simpler than in some cases than organic molecule. Okay, so these are some of the very important material characteristics which as chemists we generally utilize for obtaining stable or tuning the band gap and a lot of other properties. But definitely one of the major challenges or one of the major drawbacks that this area is facing, and that is limiting the commercialization over the years, is because of the poor stability that is perovskite based materials are known to have. So this crystal structure usually it is not very stable in the presence of either water or oxygen, and the metals that are there, they interact with them, they form their salts, various salts, and they usually degrade very quickly. In fact, though this is a drawback, in fact that's also an effort, as I mentioned, from the ministry, to ensure that whenever we utilize this kind of metals, there should also be a response or a possibility where we can recycle and reuse this material. So this poor stability, in a way, it is also helping to recycle the material or get back the materials, especially the lead that is used extensively in this kind of devices. So it is quite easy to extract them from the device. But however, to get higher efficiency and commercialization, we need to make these devices to a level where they're stable, and later on we can think about extracting them. But in addition to the water and oxygen, these devices are usually placed in the sunlight, and the UV light that is there, that also tends to degrade the device. So you also need to have a protecting layer, which helps in stabilizing this device. Finally, the third aspect, certain parts of India, the western and the northern, the southern part, definitely, you have very high temperatures, going above 45 degrees, so that also sometimes influences the performances and the stability of the device. So we also need to find out methods where we can stabilize this the device and protect the device from the heat, so that they are or make materials which are resistant to heat, where and the performance is not influenced by very high temperatures. So in this ABX3 structures, you have this A, which can be this methyl ammonium, or you have the structure of the formamedium, which is very very common, or you can also replace them with either cesium or rubidium, or it can be a mixture as I've shown below. You can have an A1, A2, or any of these. You can have A1, A2, or A3. So you can have a combination of any of these with one of these B, either the lead, the tin, or the germanium, or it can also be a mixture again. Okay, so you can have B1, B2, you can have B1, B2 here, any of this combination. Plus, you can also have this X3, so it can be a chloride, a bromide, the iodide, or it can be even be again here, same thing. It can be a mixture. So overall, the active layer, that you see here, it can be an organic part. The B is usually a metal. Then you have the halides. In many cases, you can have both the metals here, as I mentioned, the cesium and the rubidium, or you can here also you can have an organic part. You can have a metal part. You can have another metal here, and then the halide. So a lot of combinations, lot of ratios of these metals or this organic part, that they are used in combination, and we may be able to generate a good device or good results with this kind of the molecules that we use in the perovskite devices. I move forward to the passivation molecules. Now, this is also part of an engineering of the devices where a lot of different additives are used to improve the stability. In this case, this slide shows a combination of a lot of small molecules. We have a lot of polymers, and we also have charged molecule systems. Okay, now in this case, you have molecules with various kinds of functional groups. You have the OH group, the COH group. The OH group, you have the amines, you have the cyano, and you have the simple thiophene, the heterocyclic systems. In this case, you have polymers, new complete neutral polymers. You have polymers with these OH groups, very good dielectric material, and a lot of applications are have been developed utilizing this. But to be very, very honest and very frank, that usually the role of each of these functional groups is still not completely understood. But definitely it is known that these molecules have the ability to go and bind with this the active layers or the molecules of the active layers or the free molecules of the active layers, which otherwise tend to degrade. So if we can use this in appropriate combination with the active layer, the perovskite active layer, the hybrid perovskite active layer, or we can replace the halide appropriately with the chloride with bromide or iodide or a combination, that's the halide engineering, then probably we may be able to generate good devices with higher performances and higher efficiencies. Towards the end of my talk, I will also talk about utilizing smaller molecules to develop this 2D and 3D graded these heterostructures, where you end up getting high stability from all aspects, the temperature, UV, humidity, oxygen, everything, and you can get very, very good results. So what is driving the industry towards this is is a lower cost. I'll not go into the details, but usually if you have a silicon wafer, a 3-inch diameter fabricated device without the subsidies that government gives, it costs close to 5,000 rupees. This data was given to us by one source from the government, in fact. And what we did analysis in our lab is that if you make 50 plus small area devices with a few millimeters, I'll be showing that in all my talks. This comes to less than 450 rupees. Its cost is exactly similar to if you make large area devices which are few centimeters square. Okay, so you can see that the cost of 10 or 50 devices is is so less compared to this, or we can say the price difference is more than close to 1,000 times the difference. Okay, these are more than 50, and these are maybe on only one device. So it's a large difference, and these are usually the molecules which are used, and we have put the cost also on the higher side, and we definitely can bring down this cost if we do the manufacturing at an industrial level, where just instead of kgs, if we go to several 100 kgs, or we can go, in this case also go and think this cost can also further come down. Okay, so this is what is driving the industry to move towards the silicon, move away from silicon to perovskite or polymer-based devices. So going towards the research, I'll not go into detail of all the data. I can see that I just have 10 more minutes with me. So in this case, we start with this MABR. We are replacing this material with in the MAPBI3. We are replacing the iodide with the bromide. And what happens is we can already see the change, the absorption coefficient, it increases. We can see the tuning of the band gap from 1.60, we can tune it to 1.66, and there's a broader absorption coefficient. This is what drives the better performance of the devices. And from a pristine device where we have a small 0.12 centimeter square device, we can reach we change the quantity of the additives from the basic device to when we had 0.1 equivalent of this MABR, we can go close to 18% efficiency. You can see a big jump in the case of polymers and all. We were close to 9%. In the case of pristine perovskite, hybrid perovskite, we are already at 14% right from the beginning, and there's a big jump already here to 18%. Now if this increases to around 0.2%, we are again seeing a drop. So in this case, when we replace the halide iodide with small amount of bromide, we are able to go higher in the efficiencies to around 18%. Similarly, when we go to large area device, 2.5 centimeter in the control device, from the 14%, we saw a small drop to around 12.28%. Whereas in the case of this, with the additive, the 0.1 MABR, we are close to 17%. So this is very encouraging to us, and that is how we move forward to utilize small additives to tune the performance of the device and see how much more we can stabilize the device and also enhance the performances. In this case, it was halide engineering. I'll now be showing to you all about how other areas or other additives also influences the performance. Now I mentioned in my introduction slides, what the passivation molecules too. So in this case, we have utilized three different kinds of molecules. In this case, if you see, you have the benzene molecule, and which are functionalized with an amine, aniline, and then you have the two these carboxylic acid groups. In the second molecule, the HIA, we have it's a phenolic molecule with two carboxylic groups. Whereas in this case, you have a chelidamic acid where you have the pyridine molecule OH, and we also have two COH group. So all of them have a functional group which have the ability to bind with the materials that are there in the active layer. So in this case, what we do is we take the active layer perovskite and we combine it. We make an layer along with active layer. By spin coating, and this is how the device looks. And the performance is the pristine. Again, there was a small drop from the previous slide. I showed 14%. It's around close to 13.6%. With the first molecule, it goes to around 15%. With the HIA, you have this 17%. Whereas where you have more functional groups. And I did not mention about the quantity, but the optimizing the quantity is also very, very important. In this case, we are crossing now 19 devices and 19%, and this is an average of around 40 devices, and the variation is not very large. And this is very, very important that the reproducibility of this study with large number of devices is very, very important. So introducing these functional groups, molecules having this functional group with the active layer and making a device, and then fabricating the device, you can definitely, this is a very good strategy to improve the performance of the device, and we can go close to 20% now. Moving forward to other systems, in this case now we have utilized various other layers on top of this. So you have the active layer. You fabricate this device with methyl ammonium iodide, and we fabricate the device on top with this with solvent additive. We call it isopropyl alcohol. And along with that, we also have three different molecules where you have the fluoride substituted at at one place. We have the trifluoro aniline, and we have the pentafluoroaniline. So aniline is substituted, the fluoride is substituted in one place, three places, and for 5 different places. And in this case, when you have this fluoride, they are hydrophobic molecules. I mentioned that earlier. And when we make a film over the passivation layer, you can see that there's a big change in the contact angle. Okay, the pristine device, and as we increase the number of fluoride, you can see the contact angle from 48 to around 73%. It changes. That means the water layer can be kept out, or the moisture can be kept out of this device very, very easily. And in this case, now we can directly see that influence, and the power conversion efficiency, it can go to more than 20%. So by as a passivation molecule, as a hydrophobic molecule on top of this active layer, that also is very, very important to stabilize the device and to get higher performances. Now from small molecules, we moved on to conjugated polymers. In fact, our group works a lot on these conjugated polymers. But in the case of conjugated polymers, what we have done is, we have not used a neutral polymer. If you see the structure of this system, it's a very, very simple system. You have just a benzene ring in the backbone. We substitute that with alkyl chains, and we introduce a molecule with COO minus Na. There are 4 of these. So this is the neutral part, whereas the terminal groups, it's an anionic polymer. Okay, so we make this system again, the same way we spin coat it. We do the annealing, and this is the device architecture. And in the case, so this is the first example where a conjugated polymer is utilized for passivating this perovskite system. So again, I mentioned about the tandem solar cell is a nice example where you can use a conjugated polymer. Though in this case, this is not responsible, it's not a good molecule known to give a very high power conversion efficiency or for solar cell. But this can be, now it's a very good hint that you can utilize now other polymer-based system along with this perovskite active layer to develop solar cell. So this is another area where a combination of 2 different technologies, the conjugated polymers, which have definitely application in other areas. You can combine it with this active perovskite layer to generate various good results, both in the terms of stability as well as the power conversion efficiency. So when you coat this, you can see already the change in this, this perovskite or the COH groups, when it binds to the metals. So I'll not go into the detail of this, but definitely, this information that it generates is a clear indication that this conjugated polymer, the functional groups that are attached with this conjugated polymer, they can bind with this additional lead or other molecules which we tend to degrade or initiate this degradation in the device. In this case, again, when we do that, and the quantity of this PHAI is very, very important. We have 0.0 a solution of 0.50 equivalent. We add that, and we are able to cross 20% if it or close to 20.17 compared to the other layers. A very small quantity is sufficient. And this is also the stability. You check the photo stability, you have the thermal stability, you have the ambient stability. In all the cases, you can see the orange line that you see. It's very, very stable for for several hours of continuous illumination under the sunlight. Okay, in the case of this PHAI, again, the contact angle that we see is, it goes above 75%, which is a clear indication that it keeps away the water. And I'll go to the details of the large area device. This was very interesting to us. We fabricate this device of 2.5 centimeter square, and in this case also, large area device also we are able to get close to 18.5% efficiency. So it's using this conjugated polymers along with this active hybrid perovskite layer. These are very interesting results, and this area can definitely be taken forward. As I mentioned, we can utilize a lot of different polymers. We are already doing that in our lab, and that is a blue emitting polymer. You can use other polymers with other colors, or with orange and red emitting, and that also will influence the optical properties of this device. So these are one of the very recent results. I'll not go into the details of this. In this case, we are using a small molecule, so 2-benzoyl peroxide. But in this case, what we are doing is like a triple passivation. In that case, we are only on the top. So we have the when I talk about triple passivation, we utilize this benzoyl this pyridine molecule. We use in the bottom of this device, of the active layer, above this active layer, and along with this perovskite also. So why we do it in the bottom? Because the device is illuminated usually from the transparent side here, and so this layer it gives a stability to even the bottom from light coming from the bottom, or the degradation should not start even from the lower layer of this device. Similarly, if you have from the top, this is where the moisture comes in contact with the device. So you have it on the top also. This is the device architecture. We have on the top layer, we have with active layer, the BP layer, and also in the lower layer. And when you test this device, illuminate this device, we are able to get close to 20.5% efficiency. Very, very good with a small molecule system, commercial molecule, in fact. And when you go for large area device, again, here also we are getting around 18.6%. So these are also very encouraging results. Similarly, the stability that we obtain in the presence of 50% this relative humidity is more than 88% of 1,000 hours illumination. And in the case of this the UV light, both in 365 and the 254 nanometer illumination, we get more than 80% stability. So overall, by incorporating these layers on the top and bottom of this perovskite, we are able to generate this or within a precursor solution also, we are able to improve the crystallinity. Overall, the film quality also improves, and we can see the performance both in terms of higher power conversion efficiency as well as the stability. So these are also a very good strategy among the very strategy I mentioned, the triple passivation to enhance the stability and the performance of the photovoltaic devices. Okay, this will be the last part. I'll not go to the LED probably because of the lack of time. Okay, now this is the 2D, 3D graded perovskite. I mentioned about the small molecule use. In this case, we use a molecule. Again, we have a system where your COH group, you have this NS3 and this, the BR. This is the cationic molecule now. I showed about the anionic polymer is a cationic system. We add it on top of this, and we see that the layer that develops on top of this is very, very useful, very, very efficient to stabilize the device. In fact, this 2D, 3D confirmation was obtained from this XRD depth profile analysis, that we did, where we see that the 2 milligram per ml, that we quote over this ABHP, that we quote over this, and we study the varying angle, incidence angle studies from 0.2 to 1.2 degrees, and we can see that there are two different layers clearly visible. So this is what we try to do. They try to explain by a simple cartoon where these molecules they sit, and close to 100 to 200 nanometer this thickness or the 2D layer it develops over this. Now what it does is you can see the contact angle that comes up in a very, very big number. In the case of conjugated polymer, we got around 75. Here it goes to around 87%. Okay, so it's a very, very high this thing, and you can see the stability parameters. It is highly stable to almost all the parameters, the thermal stability, humidity, and even the UV visible, and the power conversion efficiency from the pristine device. And in this case, we go from around 15% to more than 21%. So this is another area which is coming up in a big way. Developing this 2D layer over the 3D layer. It's called the 2D 3D graded perovskite, where we are able to obtain very, very high efficiencies. So this our work also got a lot of attention in media in the month of December, and we thank you for media, in fact, to popularize our results. And we do a lot of work on the LEDs also. I'm making a small change, but due to lack of time, I'm just going to the conclusion now. I'll skip this, but definitely somebody has any questions or any other discussion, I'll be happy to talk to them. So I'm just moving quickly through this. So overall, I hope I'm able to convince you all that both these areas of polymer and the perovskite solar cells, they're very, very interesting, and it is important to have these active layer materials, but it's also possible to modulate this active layer as well as additional layers using small molecules, polymers, and various other methods. And this is an area which is definitely very interesting to researchers in all the from all backgrounds, from chemistry, from electronics, from physics, material scientists, to how do we do this modulation of the layer. The device engineering aspect and materials development, both are very, very important to have very, very good device. And in addition to this simple device, we also have this tandem solar cells coming up in a big way, where we are approaching around 30% or probably even beyond that. And this is going to be probably the future, along with the development of these materials. So the better efficiencies we get in these two is also going to benefit the tandem solar cells. Okay, so the efforts we put in this area is definitely going to benefit the other areas also, the tandem solar cells. Or who knows, probably we may end up having 30% with only with polymer and the perovskite solar cells. Knowing what is how we have understood, how well we have understood the device, and definitely with the incorporation of artificial intelligence. And definitely this, along with the tandem solar cells, probably we also believe the same technology will be extended to LEDs and also these, memory devices, and the incorporation of these conjugated polymers for this, probably will be useful even for the sensor areas, along with, other technologies. And the healthcare is probably one of the largest area, even more than this, renewable energy, and this is seeing a very big modification when we utilize these materials in the various portable devices, flexible devices, and devices which are wearable, and probably also that can be embedded or incorporated or integrated with our organs in the body. Okay, so this is seeing a very, very big change, very, very major change for the future of this electronics. So both areas of development, the materials development and device fabrication or device engineering, are going to play a major role in realizing applications in both renewable energy as well as healthcare applications. So with this, I really thank all the funding agencies, the Department of Science and Technology. In fact, recently we have also been awarded with another project, the ICMAP, for scaling up the devices and working with the industry. Okay, Max Planck has really funded us for several years, 2 different projects, and very nice. There is a lot of flexibility in utilizing the funds for whatever purpose we need. MEIT has come up in a big way. They have set up a clean room facility at IIT Guwahati, and will be very happy to talk to people to utilize the materials to do the fabrication at IIT Guwahati. Definitely, there is also a workshop being organized by MEIT in IIT Guwahati from next week. It's called the INUP workshop, and whoever is interested, participants, please do inform us. Let us see how we can invite you to be part of this workshop and to train you all and utilizing these fabrication techniques here. And this is one of the evening photographs of one of the lakes. We have 4 different lakes in the campus. This is the administrative setup, and really a beautiful campus. In fact, our campus is open since last month, fully open. One of the IITs to all the students. We are having only now the offline classes. Okay, so definitely it's a nice time to come and visit our campus, and we'll be very happy to talk to you, collaborate with you. And this is my research group. All of them will be very, very glad to enthusiastically help you to go around the campus, plus also talk about research. So with these few words, and with this an hour's time that Dr. Siva Kumar has given, I am very happy to be part of this meeting. Once again, thank you, Dr. Siva Kumar, Madam, and all the organizers. I'm happy to be part of this meeting, and we will be very glad to talk to you all and discuss about our research as well as any other thing. Thank you so much. Namaste.
Thank you, sir. Thank you. Thank you. We have now a couple of questions we can have. Our distinguished speaker, Professor Iyer, will answer. If you have any query, you can put forward.
I can't hear.
You cannot hear, Professor?
No, I can hear you, but the question somebody asked, I could not hear. You can repeat that?
No, Professor, no. Nobody asked, I think.
Okay,
Professor,
okay.
this Rajamali is there. She is raised the hand. Professor
Hello, sir.
Rajamali?
Yeah. Hello, sir. Yeah, it was very nice presentation. I just had one curiosity question. Like you have used benzylpredene for laminating the, I think, solar cell.
Yes.
Why did you choose benzylpredene? Is there any like? What is the requirement for selecting the laminating?
One of the basic reasons, of course, as I mentioned in my introduction slide, this functional molecule which are there, there are a lot of functional groups, we really don't know what exactly they're doing, but definitely this benzylpyridine, it is known as a molecule, which is a UV absorber. Okay, that was the primary reason, but when we utilize that, if we do it, in fact, this work is more elaborate. I did not show that if we use it only at the bottom of the active layer, it is not giving sufficient result. Okay, so we saw that if we use it only as the bottom layer, or only as the top layer, or along with individually with the active layer, mixed with the active layer, it was not giving good results. Okay, so that's what I mentioned, that there are a lot of these molecules. We exactly don't know whether we have to use it in a single the bottom, top, or all the three layers. Okay, so in this case, but definitely one of the properties that is known of this molecule is it's a very good UV absorber.
Okay, so maybe if you filter the UV absorption, then maybe lifetime can be enhanced, or what's yours?
With this device, we have not done that, but probably yes, yes, it can be done. Yes.
Oh, okay. Yeah, thank you.
Thank you.
Professor, I have one query.
Yeah, please.
It's fourth generation OLED, means organic electronic state. People are now focusing on perovskite light emitting diodes.
Yes,
so how do you see this perception? I mean,
no, definitely, so this was also one of the discussion in one of the meetings, DST meetings, and in fact, that area is likely to replace. Dr. Rajamali is also there in the work on this kind of materials, the TADF and these materials. Yes, so definitely it's going to be the future of the LEDs, and this specific property, the photophysical property of the material, has to be tapped, and we need to make devices that it's a very important area. Very good question also. Future researchers need to focus on that, definitely. Okay, the fourth generation definitely is coming up in a very big way.
Yes.
Yes.
Thank you, Professor.
Thank you, Dr. Siva Kumar.
I assume that there are no more. Professor, you would like to say something? Yes, Professor.
No, I think it was a very nice that you organized, and there's a large gathering I can see. So I really congratulate you and your team to put up this thing. Hopefully, we can also meet sometime physically, this group of the organic electronics.
Yes, Professor, definitely. I mean, next time we will plan, Professor, in person in either in Puri or in Delhi. I mean, in Bhubaneswar, Puri, we can have gathering if possible. Yes.
Sure. Yes.
Thank you very much, Professor, for your nice presentation, as well as the valuable information, which is definitely triggered because most of them are our participants are MSc student and PhD scholar, early PhD research scholar. I think they will persevere research in this direction, definitely. Everybody, their minds are ignited. With this, I please join with me to thank Professor Iyer.
Thank you very much. Thank you.
Thank you, Professor.
Thank you.
Thank you so much, Professor. We'll meet in some other occasion, either here
or thank you so much.
In person. If you visit Rourkela, it will be nice, Professor.
Sure, definitely.
Yeah, we have one more co-convener, Professor Usharani Subudhi.
Yes.
Good morning, sir.
Good morning. Good morning, madam.
This is Dr. Usha Subudh.
Yeah. Thank you. Thank you, madam.
Thank you very much, sir, for your beautiful talk.
Thank you. Thank
So
you so
we
much,
have
madam,
one
for the
more,
invitation and to be part of this meeting. Thank you. Thank you so much.
one more colleague with us, Jayaprakash. He's a professor, TP Radhakrishnan student, University of Hyderabad.
Morning, sir.
Yeah, I know. Yeah. Thank you. Hello.
Hello, sir.
Hello.
Nice to
Yeah.
meet you.
Yeah.
I'm
Nice to see
from
you all.
presentation.
Yeah. Thank you. Thank you so much.
Sir, your friend
Also,
has
Justin.
joined. Professor. Yes.
Hi, Justin.
Thank you, Professor Iyer.
Thank you. Thank you so much, Justin, for all the efforts. Yeah. I also thank IIT Roorkee actually. Yeah. Thank you. Thank you so much.
I'm listening from the very beginning. It's a wonderful talk. You are always, giving a one nice and wonderful illustrative talk. Thank you.
Thank you. Thank you so much. In fact, I just add one more information. You can, three of my students are in Roorkee now. They are with Soumitra. You can talk to them if possible.
Yeah, sure. I know. I know. I'm meeting them, but maybe, yeah, sure.
Yeah, if you have time, I'll tell them to come and talk to you. Okay, so probably let us see how we can explore further research also.
Yeah, sure.
Okay. Yeah. Thank you so much. Yeah, please go ahead. Yeah.
Thank you, Professor. We'll meet sometime.
Thank you. Thank you once again.
Thank you so much. Thank you, Professor.
Thank you.
Good morning, one and all. Once again, we have now Professor Nahan Shekhar from IST Mumbai. Next distinguished speaker for this webinar. Now I request my colleague, Professor Jayaprakash, to introduce the speaker.
Good morning, everyone. It's my great privilege to introduce Professor Nagayan Shekhar. He is now head and full professor in the Department of Dye-Stuff Technology, Indian Institute of Chemical Technology, ICT, Motunga, Mumbai, in India. So presently his research activities mainly in the design of chromophores for the nonlinear optical materials. It's an excellent topic. Brief his biodata is he born in Thanjavur, Tamil Nadu. He received his BSc from University of Madras and MSc degree from Annamalai University. Later he obtained his BSc Technology and a PhD Technology in the topic of Technology of Intermediates and Dyes from University of Mumbai. And he is the fellow of Indian Chemical Society and fellow of Maharashtra Academy of Sciences, and he is the fellow of Society of Dyes and Colorists, which is established in the UK. So this is a brief introduction. So I would like to, I am requesting Professor Nagayan Shekhar deliver his lecture presentation.
Thank you very much for your nice kind words. Are you able to hear me?
Yes, sir.
Yes, sir. We can able to hear you.
Professor Iyer, Professor Parmeshwar Iyer.
Yes.
Sir, your screen is visible, sir. Can you
previous?
Yeah. Yes, sir. Yes. Thank you, sir. Thank you. Professor Shekhar, please, sir, you can share, sir, your slides.
I have to share the screen, right?
Yes,
sir. You can
please
share
share
your screen.
Share the screen.
Share windows.
Yeah, I'm just doing this. I'm just.
Yes, sir. Yes. Okay.
You are able to see the screen?
Not yet. Not yet. there are two options, sir. One is the share your computer, no, desktop screen, or you can share your presentation. Both are fine.
I think it has to be. It's from. I have to go to that. Then on share option is there.
Yes, sir. Click the share option.
Share.
Any of them you can click.
There is something like presentation mode.
Yes, you can
power
click that.
Presentation mode. PowerPoint live. Then browse my computer. This which see I have kept my presentation on the desktop.
Okay. So you do one
You
thing,
can
sir.
directly share the screen, sir. Desktop screen
Share
itself you
this.
can share. Yes.
Click that icon. Yeah, it will
Yes.
appear. Yeah, we can able to see this your computer screen.
Screen. Okay.
Yes, sir. You can minimize this window.
If you want to join the
No.
Now you can
You're able
open
to
your presentation. Yes, you can able to see that.
you are able to see the screen. Okay.
Your laptop now battery is low, sir.
Is this for us or?
Yeah, now.
Yeah.
Yes.
Yes, sir. You can able to see your screen.
Where is the charger?
Charger. Sir, you can start with the lecture.
So first of all, thank you for your kind words. I express my sincere thanks to Professor Siva Kumar and Professor Justin Thomas for inviting me to give a lecture in this August gathering. So I will be talking about the ODP dyes. They are non-linear optical properties. So the non-linear optical materials, they have a very important role in organic electronics. And the non-linear optical properties are manifest in a molecule when it interacts with highly coherent monochromatic pulsed radiation like a laser radiation. The polarization of the molecule is the quadratic linear polarizability, quadratic polarizability, that is hyperpolarizability of a molecule at molecular level is very important, so that when you use this as a component in a device, then you get the macroscopic polarization. Okay, the beta and higher order polarizability, molecular polarizabilities, as well as the macroscopic polarizabilities, they are very. Now, organic molecules are having a lot of advantages over inorganic molecules because you can very easily design fine-tune the structure. Most of the enalophilic organic molecules which are available, they are the donor pi acceptor kind of molecules. And the molecular hyperpolarizability is, it depends on the band gap, the excess dipole moment, and the transition dipole moment. It varies inversely with the band gap, square of the band gap. Second order hyperpolarizability, it varies inversely with the third power of the band gap. So in any case, the band gap needs to be extremely low, and the transition dipole moment has to be high, so it has got a direct duration. So as suggested by the Auder's model. Now all these models have come out of the perfect understanding of the interaction of the light with the matter in the from the quantum mechanical treatment. Okay. Now this band gap, transition dipole moment, the excess dipole moment, that is the difference between the dipole moment between the ground and the first excited state, all these things can be changed by properly designing a molecule. That is why the organic molecules happen to be one of the very important categories of materials which are used extensively in non-linear optics. I have given you some examples. So this donor, you can vary the acceptor you can vary. I have given some typical examples, the pi linker also. So all this have a role in the performance of the non-linear optical materials. Now these are some of the well-known non-linear optical materials. One of the earliest one is the dispersed red one. So which has got the product. Hello? The mu beta, which we always consider, the mu beta has to be high so that the non-linear optical activity is very high. So the dispersed red has got a 550. So I have given some structures. So if you move from azo to a methane structure, so it increases. And if you change the pi bridge with a thiophene, and if you change the acceptor, it keeps on increasing. So you can go up to 18,000 when you have a tricyano furan with a thiophene bridge. Now the bottom line is that you should have a very effective donor and a very effective acceptor and highly conjugated system. Now if you keep on increasing the size of the donor and length of the pi bond, then you get into many problems like the processability of the molecule, that is using the molecule practically in a device, that is its solubility, processability, and purification, obtaining the molecule in the pure state, all becomes challenge. So people always want to have all these things. There is a very large band gap in smaller molecule. Or take a donor and acceptor which are highly efficient, so that even if pi conjugation bridge is very small, you get very good performance. So the cyanine structure is again one of the very important structure, but the problem with the cyanine is it has got very low photostability, and for the molecules to be of any practical use in nonlinear optics, it should have very good photostability as well as thermal stability in addition to the processability. So the cyanine structure, I will just. So in this particular slide, if you see on the right, so this, if you take the cyanine, if you keep on increasing the length of the number of pi bonds, if you increase, you get progressively the band gap come down. But then if this increase in length, instead of doing in a linear way, if you bend and make a cyclic linkage, then the performance, the reduction in the band gap becomes faster. So by just little modification, you can go to the redshifted absorption. And in this connection, the rigidized cyanine, we call this. So the BODP is one of the very important rigidized cyanines, which has become one of the very important skeletons in organic materials. Now this here I have explained how a cyanine is as a bent cyanine, and then you can cyclize with a boron core. And on the periphery of this BODP, you have a lot of avenues to put in a lot of substituents, so that the fine tuning can be done very easily. Unlike a regular classical donor chromophore, a cyanine chromophore, a BODP chromophore, which is a rigidized cyanine, cyclic cyanine, we can advantageously you can design the molecules. Now, if you look at this BODP core was developed in the context of evolving very good laser dyes, because they are all fluorescent. So they have very high emission content efficiencies, high molar absorptivities, and typically any BODP dye will have very sharp absorption as well as emission. And the absorption emission, it follows the known rule that they are the mirror images, and they are very robust. And since there are a lot of you can make peripheral substitutions, you can change the solubility, and they also have the high thermal and photostabilities which you need.
अच्छा 3:30 बजे से है.
Since it is not the conjugation length is not too long, the intramolecular charge transfer characteristics is a bit less here. So the hyperpolarizability values are low. In spite of all kinds of attraction what we have, this particular point one needs to address. And as I mentioned to you, the early BODP dyes, they were all laser dyes. These are the 6 commercially important laser dyes which are developed. And looking at the advantages, properties of ODP dyes, people wanted to, as early as 1996, people measured the 2-photon absorption excitation properties of the ODP dyes, and it was found among the series of dyes what we know, which are all fluorescent, ODP has got the highest performance as well as the 2-photon excitation. So this triggered the interest that one can use ODP as a non-linear optical material. To understand the performance of ODP dye as a non-linear optical material becomes a bit difficult, though it shows very high 2-photon, very powerful 2-photon fluorescence excitation. To understand this at a molecular level becomes a little bit difficult. You have to perform the experiment. Simpler experiments will not give you any result because it doesn't show any solvatochromism. So you cannot use the solvatochromic technique to understand and to screen the molecules. One has to really synthesize and do. And once it was established that it has got very high level of nonlinear optical properties, people initially started using this in biology because there you have 2-photon excited fluorescence for imaging purpose. Say for example, you can have a thiazino group, you can conjugate this with a protein. You have a carboxylic acid group, you can conjugate with a protein. So immediately after after a few years, people realized this can be used in biology. Okay. So in 2006, there was a very interesting paper in JAX, so where you can do the imaging of cells using this 2-photon active molecule. And simultaneously or subsequently, people started introducing this ODP core in a polymer backbone so that you get a material which has got the nonlinear optical properties. These are the, I think, 3 early papers where they used ODP core in a polymer and used this as a material in nonlinear optics. And this triggered interest. So as I told you, in I think here the just 1 minute. The materials what we use in nonlinear optics, they have the donor pi acceptor configuration. So to have this kind of donor pi acceptor configuration in ODP, you need to have ODP as a central core which is highly electron accepting, and then on both the sides of it, and you start introducing the donor acceptor system. These are the systems which were studied. So you have got a lot of cyano groups at the 2 position, and the intrinsic hyperpolarizabilities were measured, and you can see you can reach up to the 2050, one of the highest, the intrinsic hyperpolarizability what we can have in an organic molecule. And for a molecule to be active as a nonlinear optical material, other than what Auder's model say that you are the band gap, the transition dipole moment and the excess dipole moment, you also need to have 2 important things. The molecule as such should be totally non-centrosymmetric, which is accompanied by the non-centrosymmetry of the charge distribution. Any one of these. And also when you make a prototype device, when you keep all these molecules in a polymer, then you should have non-centrosymmetric crystallization or non-centrosymmetric distribution of the molecule within the system. Now you see this molecule, one of the very early ODP molecules, the earliest set of the ODP molecules. Sometimes you have got the centrosymmetry, sometimes you don't have the non-centrosymmetry. But there's a general trend that I think the molecule which has got that 4600, the highest the intrinsic hyperpolarizability, you can see this highly non-centrosymmetric. Because the kind of substitution, donor acceptor substitutions are totally unsymmetrical. It is one. 2 and 6 positions are supposed to be very highly symmetrical. No, it gives a symmetrical body P, disubstituted body P, and this is the totally unsymmetrical body P, which gives you the kind of hyperpolarizability it increases in an acidic environment, which says that if you put it in an acidic matrix, you can definitely have a very high value of beta. And inspired by this kind of things, we were really very active in the body P area. A few years back, we were making a lot of laser dyes to the Department of Atomic Energy as the import substitute. So we were interested in constructing some of the body P molecules which will have very high nonlinear optical properties. And looking, keeping this principle that's having the centrosymmetry in mind, we synthesize these molecules where we have the benzyl linkage here. So this was published by us in the year 2017. So this is totally an unsymmetrical body P, which has got reasonably high value of the intrinsic hyperpolarizability. Actually, under the same conditions, the dispersed red one does not have this much value. So we were encouraged that we will develop this kind of molecules. And subsequently, we synthesized several molecules and studied their nonlinear optical properties by Z-scan, as well as using very simpler method, just initial screening using solenochromism. And then, since some of this, most of the body P dyes are not solenochromic, we used extensively the density function theory computations to ascertain the nonlinear optical properties. And we synthesized if you look at the commercial laser dyes, there is one dye which has got a very powerful electron withdrawing meso system. So we wanted to have, if at the meso position, if you have electron accepting group, then you get very large redshift in the system. So we wanted to have such a functional group combined with the excited state intramolecular proton transfer property, and then we wanted to study the nonlinear optical properties. Surprisingly, we observed that when there is an excited state intramolecular proton transfer, we could not get that kind of the beta value, whereas when we block this by methylation, twice enhancement of the beta value. A simple body P, the bisbenzyl body P, has got very high. This was also prepared by us in our group. Has got very high. Then there are so many such examples in the literature of the non-linear optical properties of body P. We have also made, I have not shown all the structures here. We have made bis-benzimidazole, monobenzimidazole, bis-styril, symmetrical bis-styril, unsymmetrical bis-styril, all kinds of things we have made, and we have extensively studied using the density functional theory as well as by measuring the second order susceptibility using Z-scan. And in recent years, instead of having the donor pi acceptor, the donor sigma acceptor kind of molecules are being developed. And this, with a silicon bridge, these kind of molecules give very large hyperpolarizability. And we are working in this area. Now, recently, we have started working in this area. I think with this, I would like to conclude my talk. Of course, there is something like two photon absorption, the third, there is gamma and all, but those things, those kind of compounds which have the gamma, high gamma values, they are not that much used in organic electronics. They go in the bioelectronics, that is the biological imaging. So those things also we made, but I have not included those things in the presentation. We are currently working on the donor sigma accepting kind of the bodies. This is a very short, I have made a very short presentation. If you have anything to ask me on the nonlinear optically active body piece, I will be pleased to answer.
the presentation is now. You can have any queries or doubt, we can clarify with Professor. Professor, this ODPY has been used for NIR emitting region, like. So
Yes, they can.
How do you see this one, Professor? I mean, what is the?
Actually, you can very easily tune the emission characteristics to the deep red as well as the near infrared region by creating the benzo-fused ODP or extending the conjugation from the 3 position or 5 position with styrene. But the 2,5 with styrene is used for the nonlinear optical properties, but other near infrared active compounds can be made, can also be made. And instead of just ODP where you have got meso electron withdrawing group, if you put a endocyclic nitrogen at the meso position, so it becomes a ASA ODP we call it. So just a family of another kind of different family of ODP. They are also used extensively in in near infrared absorbing dyes, and particularly in photodynamic therapy and imaging they are used. Because in photodynamic therapy you need to have the absorption, because you have to work in with the biological window they call. Because if you have the absorption emission well within the visible region, then you have a lot of interference.
Participant, please mute yourself, please. Yes, Professor, continue.
Yeah. So the near infrared emitting ODP dyes, there are hundreds of near infrared emitting ODP dyes available. This is one of the very major areas that are in this, and we are also working in the near infrared absorbing. And we are particularly working on the DFT computations, which give a lot of challenge when you have the absorption in the deep red and near infrared region because of the conical intersection and all. So we have been working on that now.
Any other question, please? Audience may raise your hand.
Actually, the field of nonlinear optical materials, as far as the ODP is concerned, is a highly emerging field. So I think that's why the presentation is a bit short. Yeah, please.
Yes, because this all, I mean, has a lot of potential. I mean, in case of LEDs also, like NIR LED, yesterday we were talking, all of the speakers were emphasizing NIR LEDs. So these dyes, whatever you talk, it will be definitely will be important in this perspective.
ODP is definitely a very versatile core where we can very easily go to the near infrared region. Very easily. Just by putting a few substituents, we can get a near infrared absorbing as well as emitting dyes.
So if there are no questions, please join with me to appreciate Professor Shekhar.
Thank you for.
Thank you, Professor. We invite you also to visit NIT Rourkela. It's other part of your end of this side. So whenever you get chance, we will also invite you the next forum.
It's a pleasure. It's a pleasure.
Yeah, thank you, Professor Shekhar. Thank you, Professor Shekhar.
Thank you.
Professor Justin is here, Professor. Professor Justin.
Yeah. Thank you.
Yeah. So we have next speaker, Professor Anandan from NIT Trichy, very distinguished speaker for working on the renewable energy. It's my pleasure to invite him for this webinar, sir. So I request Professor Usharani Subudhi, co-convener of this unit, to webinar to introduce Professor Anandan. Please, sir. Please, madam.
Thank you, Professor Siva, for this opportunity. And good morning, all. So, first of all, on behalf of the committee, I welcome Professor Anandan to the platform. And it's actually a privilege to introduce Professor Anandan. Professor Anandan is a professor in the Department of Chemistry, NIT Trichy. He did his BSc, MSc, and also PhD from University of Madras. After that, he has several postdoctoral experience, and also after joining as a faculty, he has visited various international universities as visiting academician and visiting scientist. He has various awards, numerous awards actually, I should say, prestigious awards to his credit. And he has handled more than 22 research projects, high-end research projects. He has published 323 research publications, 21 book chapters, 2 patents, and also has trained 21 PhD students, and at present 8 PhD students are still working under him. His research area spans sonochemical synthesis of nanoparticles towards energy storage applications, electrochemical and fluorescence sensors, dye-sensitized solar cells, organic polymer solar cells, synthesis and characterization of nanophotocatalysts for the study of the decomposition of inorganic and organic pollutants, generation of hydrogen fuel using semiconductor nanoparticles. Actually, his biodata never ends. It's a very long biodata, but I have shortened it to include it within a short span. So with this short introduction, I welcome Professor Anandan to present his presentation today. We'll be delighted to hear to you, sir.
Thank you, ma'am. Thank you, ma'am, for your kind introduction. Also, thank you, Dr. Justin and Dr. Siva Kumar, inviting me to deliver a lecture in this webinar. Almost last 2 days, I saw most of the presentations are completed. Now I have to attract the students in different manner actually. So I don't know, madam, something happened when I put the open the screen. It will be some issues. It's blinking actually.
It's actually a plain screen what we see.
I shared, but blinking actually.
Okay, sir, you try moving your slide.
Yeah, now it's okay. Now it's okay, ma'am.
Yeah, it's visible. Yes,
yeah.
Please go ahead, sir.
Okay, yeah. So, yeah, please. Okay. Now you can view the screen. Hello.
Yes, sir. We can see your screen.
Okay. So thank you very much for the to invite me to deliver lecture for the open forum of webinar. So my topic will be insights into two-dimensional nanomaterials for Dyson solar cell. I concentrated on Dyson solar cell, but when I saw yesterday 2 lectures, I think I will give some important information about organic solar cells, which we also done earlier. And now, due to the efficiency, we just skip to the organic solar cell and move to the concentrate more on Dyson solar cell and perovskite solar cell. So just I give some introduction about solar cell and also come to the topic actually. So we know Earth receives 1.75 10 power 17 watt. So but most of sun solar energy will be waste actually. But we need only 47% of solar energy to get our day-to-day energy life. To get our energy, that is 4.4 into 20 joules, we need to get your energy for next 2000, between 2000 to 30 year actually. So with this view, we know PV installations in India is very, very low. So we need lot of PV installations to serve the electrical power shortage. Okay, that's what we want. So already Dr. Iyer and many people talk about first generation solar cells, second generation solar cells, and third generation solar cells. So we are now talking about a third generation solar cell. The first one is organic solar cells, which you want to talk about a few slides, and then I come to diced solar cell later. So in the case of organic solar cells and your OLED, okay, because the webinar is mostly talk about OLED and organic solar cells, just the opposite. So organic light emitting diodes are similar to your organic solar cells. You can see it consists of glass substrate, okay. It consists of glass substrate actually, okay, and then it has the ITO. Hello. And then we have an active layer. We have active layer that is the polymer we have put here. And then we have a counter-electrode aluminum over there. So in the case of organic solar cell, the light energy, organic layer absorbs light energy and we produce electricity. Whereas in the case of OLED materials, organic materials emit light energy, apply current and emit light energy. There's a difference we can see between the organic light emitting OLED and your organic solar cells. So in the case of organic solar cells, people do by different types. One is called bilayer heterojunction, other is called bulk heterojunction. So bulk heterojunction is the one where the electron transfer is very smooth actually, you can see here. Whereas in the case of bilayer, it is not smooth. Okay, it is not smooth actually. So people are concentrating on bulk heterojunction to smoothen the electron transfer process actually. So with this few introduction, we will show a fabrication solar cell. You can see here. This is the one we fabricated in our laboratory with the help of Professor S.S.K. Iyer in IIT Kanpur. You can see here, this is solar cell. Okay. So this solar cell is the organic molecule. We use organic polymer molecules. I'll come later to the polymer molecules actually. First we take the FTO or ITO glass plates and then we do patterning like this. You can see the patterning here. We can do patterning this one. And then we spin coat the organic material, that is first product PSS, and then our active layer, the polymer which we prepare, the donor polymer or acetate polymer, whichever we do actually, and we spin coat, and then we put a calcium coating or aluminum coating over which actually in this layer actually, and then we encapsulate and we get a solar cell. You can see here, this is a solar cell we can do here, and size will be active here will be 0.25 cm². So we did this here. We prepare this polymer in our laboratory, but we did this work.
Sorry to introduce, interpret.
Yes.
Professor, your slide, you are in first slide or which slide, Professor?
I am the fourth slide. That's why I think I asked you earlier also. Now?
Yeah. Now we are in the second. Yeah, now moving.
Okay. This is this is the one I showed you because when I put the full screen, it is not moving actually. I don't know what is happening there.
Sir, you have to share the window, Professor, not the slide. You just go to the, once again you minimize, I mean, then you go to the share mode.
Okay, then once again. Share, okay. Then.
Windows.
I just put window on, see, only window and then I open
screen, Professor, screen. You share the screen, not window.
Screen,
there are two options, one is screen, yeah. Screen, then now you can open it, your presentation. Now we are able to see your screen. Yes.
Now?
Yes.
Now you can see the full screen?
Now you can make it full screen now.
Now okay?
Yes. Then go to the second slide. Yes, Professor. We are able to see you. I mean, see the second slide now.
Okay, no issues. Okay. Sorry. So this is just I give introduction. I just moved to the bulk heterojunction where the movement is easier. OLED is just opposite of your organic solar cells. The organic solar cells active material absorb light energy, whereas in the case of OLED, active material emit light energy. That's a just difference. Okay. And then I just go to preparation where I can show you I showed you this one preparation. First we do patterning. okay, and then we do the coating of first material, the spin coating petard PSS, and then we coat your polymer material which you prepare in a laboratory, and then we coat aluminum on the large wire, and we take encapsulant and we make a solar cell here. Okay, this is the one. So what happened here, you can see generally most people use polymers, fullerene type. Fullerene types of polymers are mostly used for these organic solar cells, and they choose some other base materials like P-type or N-type materials. So what we are doing in our laboratory, I just show you before that. So this material, how they can produce electricity. So in the first one, the absorption light energy by your organic polymer, that is your donor. Donor will absorb the light energy from the scan and then separate your holes and electrons. And these holes and electrons migrate towards the acceptor layer. So you can see migration towards the acceptor by diffusion method. That's where bulk electron junction passes. And then bulk reduction we can check, then we have charge separation taking place. So we can see due to exciton dissociation charge separation taking place, and then we can see the migration move toward the other side. Thus we can get a current actually, and inside the film we can see the molecular film how they are inside actually. We can see by a confocal microscope and AFM microscope we can see actually how they are being. With this you can see current is produced in your system actually, okay, that is the process. So last 2 days you are attending the lectures, most of people use donor polymer and Axara polymer, even Professor PK Iyer also choose some different polymers, P7 something he told, many polymers used actually 18% efficiency. So we also prepared laboratory donor polymers using a, we can see oligobenzothiophene moiety, organic polymers. And we can use also electron acceptor spirulina. Generally, if you use donor polymer as oligobenzothiophene, people use acceptor maybe fullerene types. But we don't want fullerenes here. We want non-fullerene based material. So we prepared both the donor and acceptor in a laboratory. And one is called peri. We can use your perylene based acceptor polymer. So very important in the perylene based compound, we have positions here. We can see this is the peri position, and this position is called Bay positions actually. So we shift the molecule in peri and Bay positions, and we can prepare different polymers actually, and we find the band gap will be low or medium band gap levels. So it may be around 1.73 to 1.4 or something we prepared actually. So these polymers can absorb most of light energy and we can get organic solar cells. So we prepared a laboratory. So for example, we choose one of the polymer here, a peri-polymer, that is a perylene diamide based. Very important here, with the perylene diamide you can see this O. This O will be your peri position of this perylene diamide, and this is called your Bay positions. Okay, this is called Bay position actually. So we want to change the groups in the peri and Bay positions. So we change this O by image groups. Okay, we change this O by image groups. Different images are prepared. Okay, and we also change your Bay positions by acetyl oxy group, and we get 5 different polymers. We do a lot of work in this actually, but just I show only the 5 different polymers we prepared. And when you prepare polymer and we just look into this stem and stem image actually, we see the wrong rods. We think that this is only a polymer, but this is a wrong rods are seen in the stem image. So we have not understand how this is possible actually, and we confirm this possibility because of these image groups and also these cycloxy groups. So this group, that means inside perylene group will act as a hydrophilic part, and this R group, image group will act as a hydrophilic part. Due to this hydrophilic and hydrophobic part, there may be a lamellar aggregation. We call this is a X-type lamellar aggregation takes place in this material. Due to this, we can get the rod morphology. So this is the projection we put here. Due to this hydrophilic part and hydrophilic part interaction with the molecule looks like a rod type molecule actually, and therefore it becomes H-type aggregates lamellar structure. So we think this one actually. Okay. We just do the invisible spectroscopy of the 5 different polymers. When you see these 5 polymers actually, it shows absorbance in the region. When you change the image groups, it may be either blue shifted or red shifted. Due to the position of image groups, it may be either blue shift or red shift takes place. But we can't assume the compound may be aggregation takes place. So we do this one by solution method. Within we can do this one by methylene cyclohexane as well as chloroform in solution method absorption. As well as we can do film method, spin coating film method. We see the peaks will be blue shifted when you do this by spin coating method. So then why the spin coating method will be a blue shift actually? We want to confirm this. We do fluorescence. Before, when you do fluorescence, it shows a red shift actually. But when we do this one temperature dependent absorption spectroscopy, we notice this compound. We can see here, this is seed PDI. The seed PDI shows some extra peaks when you do temperature absorption. When temperature absorption takes place, this compound show redshifted and new peaks are formed. So this will be due to the laminar aggregation of the molecule. Due to the laminar aggregation of molecule on the spin coating on the glass plate, it shows some extra shoulder peaks. This confirms that maybe aggregation of molecules takes place in the system actually. And when you do the fluorescence, it shows redshifted actually. And when you do this lifetime measurements, so this compound shows the solution method lifetime less. When you go with your plates actually, put on the plates, it shows a broad spectra. With the lifetime it will be more. That shows the molecule may be aggregated more. So this is the confirmation of the system. We notice here it may be a rod-like morphology because of the laminar aggregation actually. So we confirm the absorption spectra and fluorescence spectra. We notice the difference in these peaks and we see the compound has some aggregation possible, and the aggregation may be due to the laminar H-type aggregation. Then we see this compound by cyclic voltammetry because we want to use this one for solar cell material. So it may be a reversible or not. So we see this quasi-reversible peaks are noticed in the cyclic voltammetry behavior. This shows compound may be electron transfer possible and we can make as a solar cell application. So we projected based on the material. So this very Berlin-based molecule will be hydrophobic and remain molecule will be hydrophilic, and this will aggregate like a rod morphology, and you see it looks like this one. That's the reason morphology will be rod morphology is proposed. We proposed this one and we published this one in Soft Materials in 2017 actually. Also we do some theoretical studies and we see this compound aggregations are possible and we notice the same thing actually. When we do this compound polymers, polymers are mostly insoluble. That's why we put a long group, cytoxy group and other things actually. And we want to see this compound will be coating. So we do this contact angle measurements with water and with glycerol. The contact angle measurements are different. This shows compound has a aggregation different angles actually. So this shows that compound is good for making these solar cell applications. So we did this work earlier with the help of collaborators in IIT Kanpur, plus SSK Iyer, and we noticed compound has stability and efficiency is somewhat good, but we don't get much efficiency, okay, 18 or 20. We get some efficiency which is better for publication aspect. So when we do this one, this Berlin diamond, we want to, people use donor maybe a fluorine base. So we don't want donor fluorine base, we want to combine with the naphthalidothiopene. Instead of benzothiophene, we prepared a naphthalidothiopene that is consists of two donor molecules. You can see naphthalidothiopene and another molecule TPD. These two donor molecules we combine. When we combine two donor molecules, whether the efficiency may improve or not, we want to check actually. So we combine two donor molecule and one oxide molecule in our system and make a polymer solar cell, organic polymer solar cell. So we notice the compound has very good absorption, okay, in the visible region, and also fluorescence. When you put this compound with the fluorine, the fluorescence may be twins. We can see fluorescence may be twins actually. That means the electrons are trapped. We confirm the electrons are flowing here. So the donor oxide molecule, two donor oxide molecule with fluorine base, electrons are flowing rapidly. Therefore, we prepare a solar cell using this actually. So just skip the number. And we see the morphology, it's spherical morphology. Aggregates morphology, we see spherical morphology. Then we also said AFM, you can see the morphology will be spherical, clearly noticed with the broken top with the spherical particle. And then calculation DFT calculation shows the compound also aggregate in similar manner of your H-type aggregation, similar type. And if we put a solar cell in this case, we get efficiency very less actually, but we see the compounds are projecting as a good material for applications. So since this material, because we don't have facilities to fabricate solar cell in our group, this polymer solar cells, we are depending on others to fabricate. So that's the reason we just dropped this research area. We are not dropped, we are just working because students also faced people's polymer, they take long time. So they are also very struggling to get these publications, high-end publications. So we just moved our topic mostly to the organic solar, sorry, dicing solar cells and perovskite solar cells now. So we just move into from organic solar cells to perovskite. So this is the one we see. We prepare a polymer. P is our polymer. The band gap banding positions are being tuned properly, and we get a good diagram and also shows a good efficiency can be noticed. That's the one part we noticed from your studies. That's the organic solar cell part. Will show due to the molecule as donor acceptor, many things playing here, aggregation type playing, and we get efficiency, etc. etc. That's it. So due to this, we don't have facilities to fabricate our own in our group actually. So we moved to mostly dice solar cell. We have all facilities to fabricate dice solar cell laboratory. So you can even fabricate 15 plus 15 dice solar cell laboratory actually. So we are more concentrating on this part actually, and I can explain more in this. So in the case of dicing solar cell, very important here, we want a transparent conducting oxide glass, FTO or ITO, and we have a TaO2 Dr. Bed technical code, TaO2 particle, and then dye, really our dye will be out in the market, N3 dye, N7 dye, etc. And then electrolyte will be liquid, and the counter electrode will be platinum. You see this material TaO2, okay, no, dye is available in the market, electrode available in the market, platinum, everything available in the market, just we can fabricate for ourselves. But research, not like that actually, we have to synthesize new material. So we want to fabricate new dye molecules, we want to make new type of TaO2 material, we want to change the electrolyte, we want to change our platinum also by other counter electrode, cheap counter electrode material. So that is the concentration of our part in our group actually. So when you do your TaO2 particle, a dye molecule absorb on surface, okay, that will absorb photons from the sunlight and we get light energy. That's the possibilities you can see here. So this is your dye, N3 dye, TaO2 will market, electrolyte will be iodine iodide in organic solvent, and they add some anic liquid because to maintain the high temperature they put some anic liquid, imidazole based, and TaO2 will be always the spherical particle mostly, and this is your N3 dye substrate. So what happens? Dye molecule absorb light energy, it pushes your electron from the dye molecule to the excited state, and the excited state pushes to the conduction band of TaO2, and there it has some problem because it has to go this side. This is like a cat in the wall. It has to go this side, or it has to come back to ground state or react with your liquid plate. So these steps come back to the ground state and return back to the reaction with your liquid plate is dangerous steps in the solar cell. It should be avoided here. And this TaO2 now go to the other side of the counter electrode to get your light energy. So once you go to the counter electrode, it reacts with your liquid electrode over there and returns back the electrons to the ground state of the electrode. So this process is continuous and we get your solar cell in a very good efficient manner. So in this case, I told two important steps. That is conduction band to the ground state of dye, a conduction band to the electrolyte is a dangerous steps. You can see here. So I just show here these two steps, that is conduction band TaO2 to the ground state of dye and conduction band TaO2 to this electrolyte is a dangerous steps which you should avoid to get high efficient solar cells. So that means electron recombination with dye molecule, electron recombination with the electrolyte. These two steps you have to avoid and tune properly your dye molecule, everything, we can get a good efficient solar cell. So that's a process we are doing in our laboratory more. So you can see the TaO2 plane in the vectorial position. It will be like a spherical. I told particles are absorbed here. So now we think the TaO2 particle are absorbed. Okay, now you know COVID reason, social distance. So particles are absorbed on the surface, what happened? Accumulate more. So you don't, electrons are not going. So we want a social distance. So we need a, instead of tube, instead of rod, instead of particle, we want a tube or wire, etc. You can see here the flow of electrons will be delayed, but here the flow of electrons will be smooth. You can see here, we can put electron, it will go smoothly in the tubes and wires, so we can get a good efficiency. So what we do, we want to make the TO to nanoparticle to nano rods or nano wires or nano tubes, then we can get a good efficiency solar cell. So you will prepare a tube in a laboratory. So you can see this is a tube image. So another important problem is the dye molecule on the surface, only particle means absorbed surface. In the case of tube, it can go inside the also dye molecule. What happened now? Dye molecules are inside the tube also. That means you can see the light will absorb more photons. That means more photons are absorbed here, and you can get a good efficiency solar cell. That's the reason tubes are much better than the particle. So that's the reason researchers, lot of researchers concentrate on work in the tubes. They prepared by different methods, soft template method, electrochemical method, many methods they are, and they prepare solar cells actually. Okay, that's the first part. We change the TO to rod, particle to rod. Second part, the dye solar cells is dye molecule. Dye is called art of solar cell. So we can see your IICT professor Dr. Segar says lot of dye molecule. They are working a lot of dye molecule, envelope particle. We also do something like that. What happened? When the solar cells, when dye molecule is not looking for solar cell, we will prepare envelope properties. So because envelope property is somewhat different compared to solar cell, if any dye which is not good for solar cell applications, we publish paper with envelope properties actually. So dye molecule should have, what happened? Injection time is very fast, and recombination time should be less. So we have to maintain a dye molecule, or we choose a dye molecule. The injection time is very fast, and the recombination time should be less. If you prepare like this dye molecule, with the help of, for example, Dr. Sorry, Justin is doing lot of dye molecule tuning actually, backup tuning actually. So he prepared lot of injection times actually, fast injection time. That molecules are much better for solar cells actually. So we also do some type of solar cell like this actually in the laboratory. Instead of normal N3 dye or N7 dye, etc., we prepared some ruthenium complex laboratory, different molecule, and we see lifetime will be very much faster. Okay, that dye molecules show very good solar cell efficiency. So we also fabricate solar cell laboratory, broad absorption, broad cruise lifetime, and we can see current voltage generation will be very high in our laboratory. So, but inorganic complexes are cyclic process, but ruthenium material you can say sometimes it will be very expensive material or toxic chemical, etc. So people are concentrating on mostly organic materials. So they choose instead of metal, non-metal organic dyes. That's called donor piling acceptor. What Dr. Segar told, people are concentrating donor piling acceptor. So a donor molecule is here, a pi linker is here, and acceptor will be a carboxylic acid base. When you view the review actually, the literature, there's people use donor pi linker acceptor. What we do in the laboratory is only one donor, one pi linker acceptor here. We tune this to different one donor, and we can choose here pi linker one side, another pi linker one side. Acceptor here, acceptor here. So you can prepare two acceptor molecules. So now you can see dye molecule anchor on surface much better, and we can get your solar cell efficiency more. So we prepare dye molecule in this, like this metal free dyes in a group, and we get your solar cell efficiency. So we get 2.37. Still, I can say this initial. This is not now. This is all published 5 years before. Okay, that's why now we are getting 9-10% efficiency nowadays, but this is initially when we have less facilities, we have only 2 to 3% efficiency we reach. So we can ask here, sir, we use metal-free dyes solar cell. We can use either the natural dyes or natural materials like your pomegranate juice, as or ivy god as a material for preparing solar cells, or a fruit extract or flower extract like red frankfurty. So we prepared some flower extract, red frankfurty, and ivy god extract from market, and we see this compound consists of different pigments like chlorophyll and anthocyanin. When you make a solar cell, it shows some efficiency, not much better, it shows some efficiency. So dye we play some role actually in those solar cells. When we choose dye molecule, all the dyes actually, what we can change the next part will be our electrolyte. So people choose quantum dots, people choose different quantum dots, cadmium selenide, cadmium telluride, etc. A lot of solar cells are there. We also did some work with this one, and efficiency increased much better. But people say this will be toxic chemical or not stable, many things actually. But still, it has good solar cells are prepared. Okay. So we now go to solar cell. Theoretically, they say 41%, 22% theoretically by organic solar cells. But this quantum dot shows 41% theoretically possible. Okay. But what we do in our part, in the next part, actually, okay, next part, we want to change the electrolyte in the solar cell. Liquid electrolyte is changed to solid state solar cell. We make a combined polymer combined with some inorganic pillars and everything. We make a polymer solar cell. Polymer electrolyte solar cell. So we choose a compound, organic compound, which is called a benzene. It's a colorless compound. When you make a polymer with benzene, actually, it undergo electron transfer. Due to electron transfer, it forms a diagonal compound, which is color is somewhat blue. So this color blue will also absorb light, and we get efficiency much better. So we notice this compound, this organic compound, very important two steps. One, it gives blue color actually. Therefore, it can make absorb more light. Second part, it can the electron come from the conduction band to TO dimolecule electrolyte. This molecule takes back once again. You can see this molecule takes back once again the electrons to the conduction band. Therefore, electron pumping is continuous actually, and we can get a efficient solar cell. So we choose this one. We find we see 3.43 efficiency with that organic molecule. Some people told we can use polymer with heteropolymaltate, inorganic compound. This inorganic compound will take PVD polymer and inorganic heteropolymer tungstate and make a solar cell using the same concept. This also plays same role. Instead of the benzene, the heteropolymer compound also absorb light energy and form an intermediate called heteropoly blue, which absorb light energy in the wavelength of 720 or 740 nanometer, which is absorb more light energy in the far visible region. That we can good efficient source can obtain. So we can get 2.7% efficient source can obtain at I don't know. In our laboratory, we prepare a lot of organic polymers, but efficiency is not getting. And also, when we make solar cell, due to last 2 years COVID, no, we cannot go to IIT Kanpur or do this solar cell. So what happened? We use this polymer as electrolyte in the basic solar cell. We prepared a polymer, same polymer in laboratory, okay? And this is a carbon-based polymer with methacrylate, and we make this as a gel electrolyte in laboratory, gel. Because solid state this gel can not operate, maybe either quasi liquid state or quasi solid state. So the electrolyte won't evaporate very easily. Therefore, we can get a high efficiency. So we can get around 8, we can see 8% efficiency also can obtain in laboratory using this carbosol based polymer gel electrolyte. So that we tune this one actually. Now, I don't know in the liquid electrolyte they use the anic liquid to maintain the high temperature. So we think ionic liquid will be much better if we prepare some molecule with ionic liquid for solar cell. So we prepare some organic compound, very cheap organic compound like S-related mercaptoprazole. When you do this organic compound, the chemistry will be first relation will go either S compound or N compound. I am not purely organic person. I just do some organic compound. So I have doubt whether this S relation takes place or N relation takes place. Then I can do theoretically with the Gaussian program. And we find the IR spectrum with Gaussian, and we see the IR will be matching with our IR is matching with your SR relation. The theoretical IR and our experimental IR is matching with the SR relation, not NR relation. This confirms that SR relation takes place in the molecule or not NR relation, and this is just organic molecule. And now we also get a crystallography and prove this is only SR relation. After that, once acceleration done first step, we do second relation here and we get a quaternary ammonium salt. Now it becomes ionic liquid. We see the melting point will be above 180 degrees Celsius. So this compound, okay, this, when we use as a solar cell, we directly put this as a solar cell. Because we use iodine, you can see we directly put your iodine as a quaternary ammonium salt. Therefore, instead of liquid iodine, we use this compound as an iodine source and make a solar cell. We get much better. We get a 414 millivolt and 4 milliamps per centimeter square current actually in our laboratory conditions, and we prepare. Still, electrolyte also plays a role. And last part, what is last part? Last part is the counter electrode, platinum. platinum is very expensive. Okay, prepare the platinum catalyst solar cell is very, very expensive. People say it's a very tough cell to prepare. So we want to make a platinum with change the platinum with other material with work function, same work function actually. So platinum has work function is 5.4 electron volt. So we want to make a equivalent work function material. So people tried carbon nanotubes or graphene sheets. So they found this platinum carbon nanotubes also similar work functions, and they make carbon nanotubes, carbon nanorods, etc. And they find the work function platinum will be carbon nanotubes will be equal efficiency 8%, 8 milliamp per square will be obtained respect to platinum. But still, carbon nanotube or graphene are expensive, okay, for Indian condition actually. So we think that we can prepare a cheap material. So first we choose a copper oxide. Copper oxide generally used in tandem solar cells. So we just take a copper oxide nanorods. We want to prepare. So we can see it's a very simple laboratory. Take a beaker, put a copper plate in an ammonia solution. We form a copper determinant complex. This is a very simple chemical reaction. And this chemical reaction after 12 hours, 13 hours, we can see we form iron oxides, color change we noticed actually, and then form copper oxides. When we take the copper plate and just see the scanning under a microscope, we see long nanorods are grown on surface. Generally, we never know them, but now we notice in the same image because of tools available, we see the nanorods are seen actually. We vary the temperature, we vary the time gap, 10 hours, 12 hours, 14 hours actually. And we see the growth of long rods will be longer rods noticed. So this copper oxide rod we coupled with your solar cell. We also confirm only pure copper oxide, no other copper metal or nothing from. It's purely copper oxide noticed the XRD. And absorptions you can see it absorbed in the far IR because the copper oxide band gap is 1.1 volt. It's a P-type material. We coupled with TO2 solar cell and we see this compound as produce solar cell electricity. So this material copper oxide, because of P-type material, volts are separated very easily, electrons separated very easily because recombination stop. So we can get your solar cell can be done possible. So we get your system. So we find the compound shows some efficiency because we use copper plate. We find. So copper plate, the other side is block the light energy. So we don't want copper plate. We want to use some other material. So we think that any two-dimensional materials or one-dimensional material or something different sheet material morphology is not needed for this to make this equal to platinum. So we choose molten sulfide. Many materials are there in the system. Metal sulfides, metal carbides, metal oxides, or metal nitrates. We choose metal sulfides. That is our molten sulfide. You can see it is transparent. We prepare in laboratory. It's transparent, similar to platinum. So this is your TO2 coded dye molecule. This is your TO2 coded FTO plate. We couple these two and make a solar cell in our laboratory. So this molten sulfide are two-dimensional material. We prepare this by taking a ammonium malate source. Okay, we want only malate. We take only ammonium malate and put the hydrothermal method. Okay, with thiourea, we can get your ammonia strand. But we want to prepare cobalt nitrate cobalt nitrate molten sulfate, nickel nitrate molten sulfate, and cobalt nickel molten sulfate. Or we want to see single molten sulfate coupled with some other material. What happened? So you notice first with molten sulfate, we notice the sheet. That is molten sulfate is a two-dimensional material. Sheet morphology is noticed actually because it is semi-image. But I can show you with the semi-image is a layered double iron sheets like morphology. You can sheet morphology, two-dimensional sheets are seen here. And sometimes we want to put some RGO also because we increase the conductivity. We do solar cell without RGO, with RGO, and we see this compound, the cyclic contaminant first, it shows a high electrocatalytic property similar to platinum. You can see the blue one is the black one is the platinum. You can show catalytic activity, nice catalytic activity, oxidation muscle. We do MOS2 also shows similar phenomena. This is the condition we need is equal to platinum and make a solar cell. When we do this one in a laboratory, we notice this one shows the efficiency of above 8%. Okay, efficiency we can get very high efficiency also can be noticed in this compound actually. So you can see here the efficiency we get here in the case of molten sulfur will be much better. So we get around 8 plus actually. So this is a one. So molten sulfate 2 dimensional nanosheets. we get a high efficiency model that is 20 and 20.5 millivolt milliamps per square, and also we can get a voltage of 800 millivolt. Very, very tremendous actually. Okay, so this is latest research. Last 2 years we published in the laboratory. So molten sulfate sometimes is not stable too much, so we couple with your cobalt sulfate. We prepare the hydrogen with the cobalt sulfate, molten sulfate. We prepare the XRD. We showed we get different sulfate source are there in the XRD, and when you prepare the cobalt sulfate, molten sulfate, we find the morphology is entirely different, not sheet morphology. It will be like a twin ball. Okay, twin ball morphology is noticed. This twin ball morphology, we prepare solar cell in our system. Catalytic activity is very good, and this is prepared the solar cell. We can get a 20.1 similar to RGO. We get a 20.1 milliamp per square actually. So instead of your cobalt sulfate, molten sulfate, we also just remove the molten sulfate and prepare nickel oxalate. We prepare cobalt sulfate, nickel sulfate. Whether molybdenum is important or without molybdenum we can prepare. So prepare cobalt and nickel first part. When cobalt nickel also we see cobalt will be twin ball circuit. Nickel will not I know it's broken structure. So nickel leads to a broken morphology. So this will give a efficiency a little less. You can see 16.1. So molybdenum is most important. Then we find combine cobalt, nickel, and molybdenum, all the three, and we make a solar cell ratio. Some ratio we maintain 8:1:1 ratio actually, and we see the morphology will be entirely different, flower-like morphology and very big morphology, mesoporous material. And these materials are catalytic activity is very good, and we see the efficiency is 15.7 maximum we get actually. So we notice this counter material are very, very enhanced two-dimensional material, enhance the morphology much better in the case of dicey solar cell. So we moved from organic solar cells to, we also continuously working. If students are interested in organic solar cell, we work actually. If also work in dicey solar cell. But now these two fields are almost 20 years old. So people are now moved to perovskite. So we also moved to perovskite. This is the application of dicey solar cell. A lot of applications given by the Great Cell group and Japanese group actually. They make bags, solar cell charger, etc., etc. Okay. So this is the one. So now we move to last part. Last two slides are there. So we move to last part, this perovskite, and we can see Professor Iyer is doing much better. But Iyer is far away from us actually because he's in Guwahati and we are in the south part, so reaching him very tough actually for collaboration. So we do some collaboration with IAC, Bangalore with Material Department actually, and we make solar cell in the group actually similar to this same material. So this dye molecule they change in the perovskite by lead atom and also they use voltage material. So what we do, we similarly we prepare same type of perovskite, perovskite in IAC Bangalore group, and we find we get an efficiency of 2.5% only Indian conditions because of the instability of your lead atom we get only 2.5%. But this is very low. We think why this material has low efficiency, etc. We want to do some switching memory effect in perovskite solar cell, and this may be due to some noise effect. Noise effect leads to decrease the efficiency much better. So we do some switching memory and noise effect, etc. with the collaborator in Italy. We send the samples to them and they do some collaborations with us, and we do this one published in IEEE in 2018 actually, some small piece of work actually. But still we are working in perovskite in different materials, but still we are lacking to do fabricate because of COVID positions. We cannot go different parts of places. So that's our research is ongoing in the laboratory. So I come to a conclusion. I thank Dr. Justin and Dr. Siva Kumar for inviting me to deliver a lecture in this webinar forum for the young minds about organic OLD materials, dicey solar cells, or organic materials for solar cell applications on perovskite. So I thank the organizers. Also, I thank my collaborators as also my students because they are the real backbone for me to give this presentation. So I thank you one and all for attending the lecture last 40 minutes. Thank you. Thank you very much.
Thank you, Professor Anandam, for such informative talk. Now the presentation is open for discussion. Any questions from audience?
Yes.
Shall I ask?
Any?
Please.
Yeah, sure. Please go ahead.
Thank you, ma'am. Thank you, sir. Really nice presentation. I want to know that you have mentioned the synthesis of the benzothiazole derivative in step 2. Can you see the slide? Benzothiazole derivative.
You can see the slides.
Am I audible?
Yes.
Benzothiazole derivative.
Benzothiazole, this derivative actually. You want this electron derivatives actually?
You have mentioned the 2 step synthesis, one and the second step.
Yeah. Correct? This one?
Still not visible. Before.
Yeah. This one, okay? You are seeing the slide?
No.
Whether you can see the slide?
No, sir.
Whether you can view the slides? Slides you are seeing actually?
Yes, slide is visible.
No,
Can
sir.
you please mention
Sir,
the
slide is
number?
not moving.
Slide is not moving. Now?
Just
Now you
below,
can move.
below one.
The previous one, I guess. Yes.
No, just.
Okay. You want the carbon? This one. I know. Which one? You want the polymer alternate? Okay, this one.
No, sir. Actually, I want to know that because nitrogen only have the valence 3 that I have mentioned, the valence is 4. So that is a salt form or what? Because you have just.
Water salt. This one.
No. Just because I need the synthesis. That's.
This one. Salt. Yeah, this is the one you're asking actually.
Yes, sir. Yes, sir. This one only.
This is the quaternary ammonium salt. We get a quaternary
salt. 1C. In the mention 1C.
1C is quaternary ammonium salt. It's a quaternary ammonium salt, ionic liquid. N plus I minus. It will be a quaternary ammonium salt. You can see here.
Yeah, I can see here.
Okay. This is a quaternary ammonium salt. Sorry.
In which condition you have prepared this compound?
Which condition you want prepare compound? Okay. This is we prepared 5 years before movie. I don't know. I will inform you. If you send me a mail, I will send me my paper to support you actually. Okay.
Okay, sure.
Yeah.
Thank you. Because I'm a little bit confused here. That's why.
Yeah, here we have prepared the condition like iodohexane, 1 iodohexane, THF reflex for 6 days. 1 iodohexane, THF medium reflex for 6 days actually. You can see we take compound 1B and reflex with 1 iodohexane.
I ask in through email only.
Okay, yeah, please.
I will ask through email only. Okay.
Okay, please.
Thank you.
May I have one
Any
question,
other question?
sir?
Yes, Vinita.
Yes, very good afternoon to all. Good afternoon, sir. I have one question on this synthetic part. Can you show slide number 2 or 3? It might be.
2 or 3. 1 second.
Not this one. You were showing the previous.
You want that organic molecule synthesis?
Sir, you made that synthesis process, no? You were showing synthesis.
Here, okay?
Yes, sir. Sir, here you told that bay positions you are showing that bay substitution you mean to say, no, sir? So there are 4 positions, sir. 1, 6, 7, and 12 position, and you made only 1, 7.
Yeah.
What was the product yield, sir?
These positions are not. You can see these positions are not bay positions. Even this is your bay
No,
position.
sir.
This is auto positions.
Sir,
You
bay
want this
position
one.
is actually bay.
Bay positions
Yes,
are bromine.
sir.
Bromine 1 year, 1 year, up one and down one. You understand?
Yes.
There will be
Yes, sir.
bromine positions are called. Yeah. Tell
Yes,
me.
sir. Yes, sir. There are 4 position, 1, 6. So we can have 3 laser isomers. One should be 1, 6, 1, 7, 1, 6, 7, or 1, 6, 7, 12. There should be 4. So how you got this only 1, 7?
Yeah, we have to start bromination. This first step here, no, this bromine will be, this place will be masked. We have to mask this portion actually, here mask actually. So we have to mask these two portions, and then we do bromination. This compound here, no, this 1, 7, the one, this 4 and 6 portions we have to mask, and then we have to do it actually. So you can see the molecules are readily available here, this molecule here, and we choose this molecule readily available molecule. Okay.
Okay, particularly 1, 7 you choose and you mean
Yes,
to
1, 7 we choose. Yeah, we don't want other positions. We only choose 1, 7 only.
Okay, sir.
Yeah.
So in your department only it is present, or economically we can buy this?
I think it's economically available because my students started preparation in this one actually by seeing some procedure, but economically it is available actually. It's available in the market actually. 1, 7 dibromobenzidine, like Berlin diamide actually. It's available in the market.
Only 1, 7 is present. Thank you so much, sir. Thank you for the information, and it was very nice presentation, sir. Thank you. Very informative.
Thank you, Professor Anandan, for such an informative talk and also for addressing the questions.
Okay. Thank you.
Thank you.
So I can leave. Okay.
Dr. Jayakumar is senior researcher in National Siva University.
So our next speaker is there, Dr. Jayakumar. Dr. Jayakumar is there.
Yes,
he
yes.
received his MSc and MPhil in organic chemistry at the University of Madras, Chennai. He obtained his PhD in chemistry from NTHU in 2014 under the guidance of Professor Cheng. Later, he pursued postdoctoral training in the same group. After that, he joined National Chiao Tung University as a postdoctoral fellow. He is currently working with Professor Cheng in the field of materials science. His research interest includes the development of new synthetic methods using organometallic compounds as catalysts and the synthesis of organic materials and application of these materials in OLEDs and photocatalysis. With this introduction, I welcome Dr. Jayakumar to start his presentation.
Thank you, ma'am. Thank you for the kind introduction about my. So, is it audible? I am.
Yes, you are audible.
Yes.
Please go ahead.
Okay. My slides are moving, so you can check. Confirm.
Yes, we can see your slides.
Okay.
It's moving. Yep.
Okay. Thank you so much. Hello, good afternoon, everyone. I'm so happy to part of this important occasion. Now I am going to present my recent research work on novel TADF material design for high efficiency OLEDs. This webinar organized by NIT Roorkela and IIT Roorkee. So before that, I will give you my short introduction about my research experience in Taiwan. So I started my career in 2010 to 17. During this year, I did my PhD under the guidance of Professor Chen Heng. Then I started my OLED research with him, and later I worked with Professor Cho Ashio and Chuang in the different field. Here I show you my PhD research experience I started my career with transition metal catalysis reactions using rhodium catalysis. So initially my PhD thesis work is mainly focused on two different directions. One is functional material based reactions, another one is natural product design. So in this first project I started in the one component synthesis of isoquinoline salt using benzaldehyde, benzamine alkynes. So three component reaction giving isoquinoline salts in the presence of rhodium catalysis. This is the first reaction ever reported in the literature. Also I published this work in Angewandte Chem. I received the highly cited paper, over 240 citations. Then I thinking on the extending this methodology to large fused molecule like protoberberine based alkalides and benzonaphthalene based functional material. So here you can see the simple starting material. I started with about 120 molecular weight. At the end we can see more than 1100 molecular weight. So these are the works I finished during my PhD, and also I received outstanding student award for this paper based on this experience. And also another opportunity work on CH activation based reactions with Professor Chuang. So in this case I designed polycyclic salts using diazobenzene as the coupling directing group and also alkene as the coupling partner. In the presence of palladium catalysis, it gives fused polycyclic ring. It becomes a planar molecule and also highly planar in the presence of palladium catalysis. This reaction required more than 4 steps to complete this reaction. So this is another one more advantage of this reaction is we can achieve efficient manner. And also because of this paper I received outstanding academic researcher award from the most. So based on this design I extended this methodology to different substitution with a different molecular containing electron withdrawing nature and electron donating group. So some of the derivatives show excellent photophysical properties such as high extinction coefficient and emission properties. High fluorescent quantum field. Based on this picture you can see the some of the compounds shown here, and also the long excited fluorescent lifetime. This one compared to rhodamine G, the well-known dyes, this is comparable to and also this one highly suitable for the thermodynamic and the bioimaging applications. So in future we are trying to apply this methodology to using different OLEDs, solution process OLED or other thermodynamic applications. So why I started my research on OLEDs? Based on the previous experience in organic synthesis and small photophysical properties application, the Professor Cheng told me to extend my career to different functional based material based OLEDs. So now day to day every life commonly used thing is the smartphone LED light. So OLEDs are popular display technology used in smartphone and television, and extensive research into making more efficient OLEDs in both academia and industry. So this is the basic principle of organic light emitting device. OLED device structure comprising multi-thin layer device that consists of several organic semiconducting layers. So, in the simplified mechanism, the charge carriers, that is the electron and holes. Electron and holes are obtained from the cathode and the anode by applying external voltage. Subsequently, the charge carriers migrate through electron transporting layers into the emissive layer, where the recombination hole electron formation of exciton takes place. The electroluminescence emissions occurs as these flex radiatively from the excited state to the ground state. So once find the topic on OLEDs, we need to take the deep discussion about what are the upcoming research. From up to now, I don't know the basic principle initially. So later on I started to study on the first generation OLED, second generation and third generation. So small introduction about the first generation OLED demonstrated in 1987. Their used fluorescent emitter was used, which limits the internal quantum efficiency up to 25%. And also the singlet, only the singlet excitons for radiative decay, and the 75% of triplet excitons are quenched by thermal radiation, which can be greatly improved to 100% internal quantum efficiency with incorporation of iridium and platinum complexes into the organic molecule, which facilitate the phosphorescence emission, which is also called second generation emitter, which has been achieved for the red and green phosphorescent OLED using this approach. However, the operation lifetime is still bottleneck for blue phosphorescent OLED due to their wide band gap and long exciton lifetime. So exciton and polaron interaction create a whole hot excited state which degrades the materials. So even though if giving the high efficiency, so